Bom dia a todas e todos. Good morning, everyone. I would like to first welcome all of you to our research laboratory. We're very happy to have you all here today with us. I'd like to first introduce myself. I'm Marilia Braga. I'm a researcher here in Ricardo's team. And today we're gathered here to discuss second life battery. A few notes before we start. We are transmitting this online, so I will ask that all the questions and all the presentations are done on mic, so we can make sure that everyone can hear us. We also have a really tight schedule today. So to make sure that we can get through this very full morning, some people will let all the presenters know when you have 5 minutes or when you're over with your time. So after the first few presentations, we're going to have a coffee break and the inauguration of a second life storage system for e-mobility. So make sure you don't miss that. And then after, we're going to move forward with our presentations. All the questions and discussions will be at the end of the day, or at the end of the morning, and then we're going to have a lunch. Of our projects. So to start off, I'd like to invite Ricardo, our lab coordinator here at Photovoltaica UFSC, for some opening remarks and give you a bit of context for this event.
Thank you, Marilia, and welcome everybody. I will be very brief. I just want to put this in a little bit of context. We are here today because we have a cooperation project that has been approved and is supported by the DAD, which is the German Academic Exchange of Germany. And the project is coordinated by Professor Sergei Dil, who will come and give you an overview of the project. It's called 2LIFEBAT, second life batteries, which is the topic of the workshop and the topic of the project that we'll be carrying out together. And it involves the Federal University of Amazonas, and we have Professor Bessa here and his colleague Alessandro. We have also the Federal Institute of Santa Catarina, Professor Samuel Abreu, and not yet his colleagues, and ourselves here at Federal University of Santa Catarina with another lab also on the main campus. So without further advancing on our tight schedule, I just want to invite Professor Dil here to show you an overview of the whole project.
Thank you, Ricardo. Can we open this presentation? Okay. No, it's not this one. Okay, thank you very much. Before I start with the review, I would like to express my gratitude to the GIZ for funding our project. Thank you very much, Pedro, for choosing our project. I would like to say thank you, Ricardo, and your team for hosting us here at the Photovoltaica Lab. Thank you very much. So, I would like to give a short overview about the project. 2LIFEBAT, robust solar-powered storage systems with second life batteries and their economic and ecological potential. What is the motivation for the project? The motivation for the project was that we would like to develop second storage systems, electric storage systems using second life batteries. Since we have a rising market right now, so for electric vehicles, and I think there could be also a rising market in the future for the batteries, which are coming out of the electric vehicles, since they have arrived to a capacity of 70%, for example, which is guaranteed capacity for vehicles. Yeah? vehicle batteries. And we would like to use these storage systems especially for the Amazon basin, where we have many villages without access to the main grid, to the electricity grid. And therefore, systems based on second life batteries might be a low solution for those people. And for using the second life batteries, so we need to clarify a few important questions. And the most important, what is the service life of the second life battery? So what is the capacity, what is the degradation of the battery, and how does it look like? So we need to investigate this, also to develop reliable storage systems, especially with regard to the climatic conditions in the Amazon region, high air humidity, higher temperatures, and of course to elaborate applications and to derive their economic and ecological potential. So when we take a close at the objectives of this project, there are many of them, like for example to investigate the aging behavior, investigate swelling behavior, elaborate housing design, and so on and so on. And this is something so where we need different partners from different universities, different experts, so to elaborate on these questions. And therefore we applied for this project, for this NOPA project funded by GIZ. And what we have in this project now, so we have 5 project partners, 5 university partners, 3 universities in Brazil, 2 of them here in Florianopolis, University of Manaus. The colleagues are here. And in Germany we have University of Duisburg. Arne Jeppe is also here with us today. So we have experts from different disciplines. And, what we are doing in this project, we establish the research cooperation. That means we are doing research transfer. We organize exchange. So people from Brazil will be coming to Germany, and also people from Germany, like us today, we will be coming to Brazil. We have student exchange. We also organize guest lectures. And I would like you, if you are interested in cooperation with us, so please let us know. You can use the email address, my email address, for example. You can just go directly to the web page of Second LifeBat, this QR code, and please let us know. The next workshop, this workshop in Brazil, consists of 2 parts. The first part is in Florianopolis, and second part will be next Wednesday, organized by Yuri and Alessandro from University of Manaus. So this will be the research workshop in Brazil, but the next workshop will be in Germany. It will be in the week from the 12th to 16th June. So it means colleagues from Brazil will come to us to Germany. And the official part of this workshop, so like this one today, will be on Friday on the 16th. So please put your calendar, and but you will of course receive an official invitation for this event later. Okay, this was short of an introduction about the project. So thank you very much. Enjoy the lectures today, and so I'm glad to have so many people today here. Thank you.
Excellent. Thank you, Sergey. And now I want to invite Pedro Rodriguez from the GIZ, who is the person behind the E2 program project that GIZ is sponsoring on this topic of energy storage. So, Pedro.
Vocês podem colocar a apresentação, por favor? Okay. Good morning, everyone. My name is Pedro, and I'm the technical advisor of the E2 project that deals with energy storage technology, GIZ. I'm very happy to be here today among you in this workshop about life battery here organized by Professor Ricardo Hu here. And today we have two activities of GIZ E2 Brazil project here in this event. One is the DAD that came from NOPA to Zero DAD project. And the other one is academic cooperation developed by the Institute IDEEE, led by Professor Adelman, Peter Adelman, that is participating online, and represented here by Carl, Emanuele, and Augusto in this event. They're going to make a presentation as well. I'm going to present to you a little bit of E2 Brazil project and the activities that we did already and that we are currently doing. And yeah, can I pass here? Okay. The E2 Brazil is a project implemented by GIZ and also the Ministry of Mines and Energy of Brazil, and it's financed by the Federal Ministry for Economic Cooperation and Development of Germany, the BMZ. The objective of the project is to create the prerequisites for the widespread use of energy storage technology, mainly to improve stability and also security of electrical service in Brazil. The project has a financial budget of 5 million euros and the duration from January 2020 to December 2023. So the project is going to end by the end of this year. We have 4 outputs. The one is to create the framework conditions. The second one is to integrate the energy storage in the electricity systems. The third one is to demonstrate technically, economically, environmentally the feasibility of energy storage in Brazil. The fourth one, which belongs to the NOPA project, is the scientific cooperation. So this is the activities that we did from 2020 to 2022. It was based on microeconomics, integration of grid and off-grid systems, and also we made a study about the impact of retirement of national coal-fired power plant as well, because we see opportunity to better energy storage systems there. For this year, we still have some activities, such as awareness raising for banks, for financial institutions, in which, if you're interested, next week we're going to have a workshop related to this. We're going to present financial lines, analysis of market, technologies, and regulation as well. Also, we're developing activities of selection of battery energy storage projects. So if you're interested, it's a public call opened, and you can apply, just send in an email and so on. And the idea is to present projects in the Smarter in São Paulo that's going to happen in the last week of August, related to battery energy storage systems. Yeah, and that's it. I'm Pedro, I'm the technical advisor. Jan Kinak is the coordinator of the E2 Brazil, and here is our mail, E2 Brazil. And that's it. Thank you very much. Have a nice event.
All right. Thank you, Pedro. All right. So now it's time for us to get started with our presentations. I'd like to first invite Arne Jeppe from UDE to talk about impact of circular economy.
Thank you very much. Thank you very much for having me here and presenting this very theoretical theme at the beginning. So I hope I won't put you to sleep. I'll just take the presentation if it works. So I'm Arne Jeppe from the University of Duisburg-Essen, which is one of the largest universities in Germany, and we do research on economic potentials and do it actually for the German automotive industry. Our chair is involved in many projects. We are quite large share for German universities, and we do a lot of projects and international projects. And as you can see here, we are doing strategic management for automotive research. So now coming to theoretical concept we develop for multi-life products. I will translate it because it's partially in German. We thought about it a long time ago, enlarge life cycles for any kind of products to reduce the overall operating costs. And this is especially important if you work in the automotive industry for batteries, because batteries are extremely expensive. And if you try to bring down the prices for batteries and you're not able to on the production side because of the limited production capacity, because it's a building market, a developing market in Germany, so you don't have enough production capacity and you don't get the resources, because limited resources because of the rare materials you use for production. You need to enlarge the life cycle to reduce overall costs in the system, to make it cheaper in every part of the life cycle. And the general thing was you gain the resources and you check them, then you produce it, and then you use it. But after the use, it's going to waste. This was the general life cycle as it's been in the last decades. Now, with the help of analyzing things, we try to enlarge the life cycle. And this is what Sergei told us in this presentation. This is showing how important the combination of economic and technical research is, because at this part you need to analyze how the state of health of, for example, the battery or other components is, and then you can enlarge the life cycle and also and achieve, we call it a multi-life, which is a new theoretical concept, which is an enlargement of second life. Second life is the first multi-life, and then it goes on to other lives. But at this stage, it's very important to analyze the state of health, giving it into a new life, and gaining new potentials from the new life, and gaining new and getting to lower the price in the new life, and then do it back and back again. So it doesn't stop with second life. We can do it again, but it's very important to have the status, and this is why it's very important to work together with the technical department. So this is a new theoretical approach for product design, which we developed. Here you got the form that the batteries are produced today. You got these things in the battery production, and this is what with the second life model. So we in the normal model, the battery is designed for a specific purpose, let's say for a car. And what's happening now with the second life approach is that you design it, you still design it for a car, but you remanufacture or refurbish it and you recycle it for a second life. And our approach is, this will also help in the project, you don't produce it anymore for a special purpose, let's say for a car, but you produce it for a longer lifetime. And this is what we call design to multi-life. And here you can see the problems start to begin, because actually if you want to reduce the overall operating cost, you need a whole new design structure. And I will show you why you need this in our results a bit later. But this is what we try to achieve in the project together with Sergey, is that you do not design something for a purpose and use it, just reuse it, but design it in especially connecting or creating special connecting points and data sharing points and state of health analysis over all time of the product. So you can use it multiple times, second, third, and whatever, to enlarge the life cycle, to reduce overall operating costs, and so achieve a higher value for these rare resources. And this will, and this is what the whole project was intended, this will have economic potential for the batteries and also reduce the ecological effect battery production because of just of longer use. So this, but this is a theoretical approach. So in the beginning, you should already think about this, and this is a new concept which has done before. It's just now we are producing for a special purpose, reusing it, and the theoretical science should be designed something that you can use it in longer terms and in other applications. We conducted some theoretical research where we had our general business model and analyzed how the effect of this multi-life will affect these categories. And then, of course, we did more theoretical research on the joint value creation within the partners, because when you develop something for a multi-life, you need partners. So we analyzed for the German battery market what will happen with the modularization and the complementarity. So with the supply side and the demand side, we also analyzed the service dominant logic as a theoretical concept where you use something together with the customer, so the customer is part of value creation. Then we analyze platform effects for the German battery market and also pricing in the two-sided market, because you just, in the new concept, you don't just only have one customer but two or more. In the second life you got two, but imagine the third life, you give the battery to the car manufacturer and after to the storage and then to whatever kind of customer. So you need to price it for every customer, which is very difficult because you have to see into the future, and it brings out a lot of scenarios. So we analyzed the company relationship and the knowledge transfer, which is a very important thing because nowadays in the automotive industry, no one wants to share the knowledge because it's part of the value creation inside the firm. And all this, if you want to construct a multi-life product, you have to gather this whole process, and we also analyze the governing of this process and how it should be done. So here I just show you the influence on the value chain. It's a normal value chain, as you all know it. You find resources, you do development, you produce it, then in the 4 stages, then you produce the battery, you use the battery, you analyze it. It's already been done today, but not the form we need. And the new part is just this hook, or as we saw here, it's better to see it as a loop to just enlarge the usage. And this is not very easy, so it looks very easy, but it's not, because you constantly have to monitor different factors. You of course have to monitor how is the state of health of battery, but you also have to monitor if you want to reuse it. You need to monitor what is the cost of refigurated to another place where you can use it and how it has to be adopted, and all the costs concerning this at this point is quite high, so it needs to be analyzed. And of course, I think we miss something here. Can you put it up? Or it's not important. It's just a formula. No one cares. So, oh, it wasn't me. Okay. So here we modeled the return for the German battery vehicle market to see what is the potential or what are the numbers of batteries that will return. And this has been done there are some formulas we don't want to talk about now. But here you can see this is a general return behavior for German electric cars. You can see most of them are returned after 8 years, and this is a very normal return rate. We analyzed it with a high number study, so we are pretty sure that this is correct. And this is the return of battery cells, which is different from the returning of vehicles because, example, for replacement batteries, accidents, and so on. So because we are focusing on the battery return, we have to not only analyze the return of electric cars, but actually the return of the batteries in the cars, which is different from the cars. And you can see the age of the returned batteries in Germany prognosed for the next 10 years. So we will have this kind of return. Here you can see the number, and it's getting quite high. So nowadays we don't have a lot of second batteries because there is not a lot of return on them. As I said, the market will just ramp up, and here you can see the ramp up quite clearly. A different kind of prognosis. See around the next 5 years there will be a lot of batteries that will return and will be able to be remanufactured for a new purpose. And we also analyzed how the costs of the remanufacturing and actually what you do in your facility by opening the Nissan Leaf and putting out the batteries and doing it to a new purpose. We analyzed in working hours, in material, and everything, and we found out that if you do it like so and you take it out from a battery that was used in a car in 2013, yeah, the first year you will have a positive cash flow is in 2032 if you do it in Germany with German work and labor costs. So it's quite ineffective. And the break-even will be in 2040. So you have, I will step aside so you can all see it. If you do the remanufacturing in Germany, it's quite ineffective nowadays. And this is even to the fact that there is no real market for second life batteries in Germany, because on the one hand the people want new batteries, and on the other hand the companies do not trust used batteries. So this is very important to work with the technical department, so we are sure that the second life batteries are also in fine condition, working as well. And to do it very, very short, you can see if you got a single life battery, the costs here, then now in Germany you get a very small block of additional revenue from using it in a second life compared to the costs of doing a second life battery because of analyzing, remanufacturing, and so is very, very small. And so we seek new potentials in other application. I see for the 5-minute warning. Actually, we use we seek for new potentials, and we see that in the use for the Brazilian market, because here we can use our second life batteries from German cars to in large numbers, because we have a large return on batteries, so we have a quite big supply, and we can use them to buffer electronic systems in the Amazonas region. And with this, we can also have an ecological impact. And we've done the theoretical framework, as you have seen, and we've done the research in Germany. And actually, I'm now here next week going to the Amazonas region, doing a survey with people living there and some guys from the electric company. So Alessandro, he was the contacts to me. So we will do the economic potential from German car batteries, which are here, which are in quite high number here, but have a low potential, a low economic potential in Germany. So we will estimate the ecologic and economic potential in Brazil, and hopefully, I hope the potential will be high, so we will find a new market for German second life batteries, and we also monitor the impact of using the second life batteries here in Brazil on the ecologic base, so also reduce CO2 emissions, and of course we also consider it if we just remove the diesel generators from the Amazonas and replace it with the combination of solar and battery systems, how the ecological impact of this will be. And also we will be publishing an article to this, which proposal has also already been accepted, and now we fill it with data and publish it, and I will share it in this community also. So thanks a lot for your time, and I hope you appreciate some insights of the German car industry, and I'm open for any questions. Yeah. Thank you. Oh, no questions. That's good for me.
Thank you, Arne. We will leave all the questions for the end of this first block of presentation, right before our coffee break. Is that all right? Now I'd like to invite Professor Emanuele Marini to the stage. He's from the Center for Solar Energy and Hydrogen Research in Ulm, and we'll be talking about advances in rechargeable battery technology for stationary applications. Thank you.
Thank you very much for the introduction. So, hello everyone. So let's see if the pointer works. So, good. Okay. So, hello everyone. Thank you for inviting me here to the organizer to give this talk. So, I am Emanuele. I'm working at the Center of Solar Energy and Hydrogen Research in Ulm, Germany. And we are focusing on different technologies, so fuel cell, photovoltaics, and lithium-ion. And in case, we also cover alkaline batteries. So, today, I'm going to talk about use cases about rechargeable alkaline batteries for stationary energy storage. So, we know that we go to a greener transition, and we need to balance between electric generation and demand. And for that, we know that we need different systems for electromobility, for households and utilities. So we need batteries in different sizes and formats to cover all these needs. And at the moment, in the battery, the most conventional one that we all know, lithium-ion and lead-acid. However, both these systems have their pros and cons. And for certain type of application, they may be suboptimal. So for instance, lithium-ion provide a lot of cycles, so thousands of cycles, high energy and power. This is nice for cars or for high power application, but doesn't make sense to have it in a big storage where we don't have so much material to give so much energy. Lead acid instead, for instance, a lower energy density, but it has also lower cycle number, and also sometimes we are a bit in concern regarding the environment, especially in those countries where we don't know exactly how they recycle this. So here, what we propose is another chemistry, is the alkaline battery. you all may know for a small portable application as a primary battery that you buy in the supermarket as a AA formats, but you know that this battery is primary, so not rechargeable. And always, often, we forget that this is also a battery, and nobody talk about it, that maybe can also be considered as an option. And this has several intrinsic advantages. First of all, this system work is based on zinc manganese, and materials are very abundant on the Earth crust, and that make it also a very cheap system. So nowadays you can buy batteries, primary of course, with prices lower than $30 per kilowatt hour, and this is something kind of unbeatable. They are also intrinsically safe. These are aqueous batteries, so they don't make use of organic components which may take fire, and they are not toxic, so you cannot burn fire. So, and another advantage of this system is that they're established, so they're around since more than 50 years, and so the supply chain is already there, and the point is how to make it rechargeable. And also, nowadays there is also several ways to recycle it, and considering that a lot of these batteries, since they are not toxic, they just get landfilled. So, and manganese is also used as a fertilizer. But this brings us to the point, let's say, how we behave in terms of levelized cost of storage. So in a study, here the reference later, you can also have a look. They compare the cost of different technologies, for instance with lithium ion and lead acid, and they show that they, in their paper that zinc-based battery can be very competitive among existing batteries. Still, the price is relatively high, but that's depend a lot on the number of cycles and the size of the system. Now, just a quick word how this battery works in just a few words. So this is a schematics of our type of type cell that you can buy. So at the center, you have this needle, which is the current collector for the anode, the zinc anode, which is paste, and is it this white part. And surrounding it, you have darker side, which is your cathode, which is the manganese dioxide in rings. This is another schematic, just kind of a cross-section. Here you have this needle, here you have your zinc particles, then you have the separator and the manganese dioxide. And during discharge, the zinc, the metallic zinc, oxidizes into zinc oxide, and you have, by withdrawing the electrons, they reach the cathode, and the MnO2 get reduced. Here, a couple of electrochemical reaction. In practice, what are the specs of primary batteries? So they provide a voltage of 1.4 volts, and this thing is very known, but maybe not everybody knows that it has a very high energy density. Still, now not at the level of lithium ion, which is more in the range of 200 watt-hour per kilogram, but it can be very competitive, considering lead acid that we are in the range of 60 watt-hour per kilogram. The power density, though, is relatively low, so what I mean, this is not now a battery that you're going to put in a car, but it may be very some potential for stationary storage application. One point that is important to mention is that this value are given for just partially discharged battery. When your battery reach about 1 volt, it's usually stop working, but basically what is used is just half of the capacity available. And this is just because the small portable electronics work within a certain voltage range. But if you want to access all the capacity that are available inside the battery, you can even double the energy density into this. A little summary of the history of this battery. So it's not new, as I mentioned. Primary battery exists since 1950, and already in the early days, some veterans tried to make it rechargeable in the 70s and the 60s, but they failed because they were very limited in recharging the battery. They just achieved a few cycles. Then, a few years later, they tried again. They improved a little bit the chemistry. In the 1990s, they were able to license this technology to Rayovac. And to the name renewal. And here I found some nice advertisement of those days where they were trying to short his battery for portable electronics, and he had even his own recharging system. So for small type of technologies. However, in 2000 they had to withdraw or discontinue the production because in that days it came the lithium-ion nickel metal hydride, and again the number of cycles were not competitive at that time. So they just had to discontinue. But now, after a few years after, people come back with proposing big system, again based on the same technology for large-scale stationary storage. And one of these companies is the Electric Power from US, which just funded their company, and they promises a large-scale system with several hundred of cycles at a relatively low cost. But this is nothing else than the same technology. They just reduce a bit the depth of discharge to get more cycles. So from their side, there was not any further technological development. It's always the same thing. So, but why this battery is not rechargeable? And the problem is mainly related to the discharge products generated at the zinc anode. So when you discharge your battery, you cross these zincate ions that cross separator, reach the cathode, and contaminate the manganese dioxide, forming the so-called etherealite. And here I show one of our experiments where we prove that zinc is the problem here. So here we have the capacity retention as a function of cycle number. As you can see, in the absence of zinc in the solution, your battery can cycle reversibly 100% for forever. No kidding, but for a very long time. So when you put zinc, just a very small amount, you can see that the capacity fades very quickly. So just after 10 cycles, your capacity drops by 20%. And this is because this fade is irreversible and you cannot bring it back to the original manganese dioxide. So the strategy is to find a separator or like an electrode design that is able to block these bad species and keeping at the anode side, but while letting the other species cross in the membrane and let the reaction occur. And this is exactly what we did in the last 2-3 years at CTSV. We developed electrode design that enabled to achieve this. So even at very high depth of discharge, which even 100%. So here we compare the performance of the charge-discharge profile of a conventional battery. And you can see in the first cycle, you have the very normal behavior, discharge. This is the first charge, but then you see a very abrupt decrease of capacity with cycle number due to the problem described before. In our new design, instead, you can see that the profile, the discharge and charge profile are retained and even improved with cycle number. This is also showing like the stability of our battery. So this is a system that you go at relatively low discharge rate. So for one cycle, it takes 20 hours. And here you can see that this is showing the capacity versus cycle number. This is the nominal voltage. So you can see that we were charging at 100% depth of discharge, and we basically had no change of capacity over more than 190 days testing. And this was just some tests that we performed to see how the capacity change at different C rates. So as I mentioned before, where are we now with respect to lead acid and lithium ion? So this table has been provided by our friends Urban Electric Power, are producing this type of battery already, and they presented this in 2021. So keep in mind that the number may be not really updated to today's values, but already at that time, a small company, they were able to sell the battery at a price of about $200 per kilowatt hour with a very small factory. And at that time, lithium ion was competitive, better than today's. So now if you would consider the price of Tesla Powerwall, it would be already, you may have a better number than me. And lead you can see that we are very close to zinc manganese. What is very important here, an advantage of this battery is the self-discharge rate. You can see that we typically have below the 1% per month. And this you already know when you buy alkaline batteries, those discharge rate, you can keep the battery for 10 years and you can still use it. And because this is the same chemistry. And this lithium ion and lead acid are not that good to this. The warranty you can consider as a, let's say, the number of cycles. At the moment, we can say that they have similar cyclability as lead acid, not like lithium ion, but this is something that we are working on it. And last but not least, the fact that the battery is intrinsically safe can be very advantageous for an application. Again, here we put it together a small table showing the stock prices of the different metals. If you want to talk about lithium ion versus this type of battery, you can see that typical elements containing high power density lithium ion, cobalt, lithium, and nickel, you can see the fluctuation. So now there was a bit drop of the price of lithium, but I really don't like this volatility, whereas zinc and manganese, since they come from a very long tradition and supply chain, you can see that they're part of their very low cost, also their fluctuation is relatively small. Okay, but based on this, what could be the application of our batteries? So one use case that we were thinking about would be the telecom market. So we know that different areas, very remote access, where you may want to have better connection for your phone. You don't want to stay without the possibility to call your friends and parents. So we want to put antennas there, hopefully. But at the moment, the market is saturated by lead acid and lithium ion. But we may think that in this area, in this remote access area, we have large fluctuation of temperature and humidity. And we know all that lithium ion and lead acid maybe suffer this condition. And because you need maybe climate control, sorry, and like this. Zinc manganese are very reliable. It's also able to operate in a wide temperature range. So between -30 or -40 plus 60. So I would say that would be also nice for steel. The point here is now how much we can reduce the cost of our system. But we believe if we can target a cost lower than 100 euro per kilowatt hour, we have a good chance to penetrate into this market. The second use case, the uninterruptible power supply. So you already know, now we are facing a growth of this data center where we need more and more power, and it would be very bad if with a shortage of electricity or a blackout, we cannot power this system anymore. At the moment, as a generator, there is maybe diesel or mainly acid, and there it's a no-go to have lithium ion most of the cases because it's classified as a hazard. So if you would have a runaway of this battery in your data center, it's not good. And here, Urban Electric already demonstrate with their battery, with a very small dip of discharge, that they can compete with lithium lead acid battery. So they place their zinc battery, replace lead acid, so they occupy the same space, but they can already provide 6 times more time of energy for the same space. Again, this is very important to keep in mind that we need to reduce the cost of this system. Last but not least, let's say I borrowed this slide from Ricardo, thank you, from his last presentation in Augsburg in Germany, where he talked about the situation in Brazil with this remote access area, where they are actually have using, please correct me Ricardo, also diesel generator. So for a very small part of the population, about 1%, they spend a lot of money to keep this remote access area some electricity. So we may think of giving part of this electricity in terms of our battery. So, thank you. Second application, or let's say thing that would be very interesting, would be related to the reliability of your grid. So Ricardo showed us that in Brazil you have 40 hours a day of failure of the grid. And if you compare to other countries, this is a very important number, and you have to keep in mind that maybe for a hospital or place like this time could be very, very critical. So what you can think of is of having a battery that and cover this type of electricity until the system is into place. This is my last slide. So this is exactly the application that we are meant to apply in the future, which is the residential market and the grid scale. So we have at the moment identified 3 types of storage. One is seasonal storage, where we want to have a huge battery. This could be interesting for Germany, for instance, where you accumulate the energy with the photovoltaics during summer and then release it in winter, where you don't have enough energy to supply your home or your facilities. And this would be a battery that would have a capacity of about 70 days. So, and you would do basically 2 cycles a year. So this would be the goal of this battery. Weather would be maybe interesting for Brazil, where when you have this failure of the grid, you want to have a battery that can maybe work for 1 or 3 days in a way that it let people repair the grid, and so you have a coverage of this time where you want to power your home. And for that you would need a relatively big battery, and considering our cost, I think it's feasible. And day and night, it's like daily use, you would need about 350 cycles per year. This is something still running in trying to find out if our battery would be suitable for that. Because that if you want to have 10 years, you can see that we are more in the range of cycle number that lithium-ion is good at. But what I want to say is that our friends, Urban Electric Power, already demonstrate that battery can be used for this application. And now, if we are going to be able to apply this high dip of discharge, we are going to be very good, in a good place for also apply our battery for this type of technology. So with this, I want to thank you for your kind attention and again giving me the opportunity to present here today. Thank you very much.
Thank you, Emmanuel. Now it's time to invite Professor Sergey from TU Ingolstadt back to the stage, this time to talk about the development and testing of batteries for the automotive industry. Thank you, Sergey.
Thank you very much for the introduction. So we need to wait a few seconds until the presentation is open. But please not the PDF, please open the PowerPoint. Okay, thank you very much. So as I explained before at the beginning, so for the stationary storage applications, we would like to use automotive batteries from previous use in vehicles. And from my point of view, it's quite important and interesting to know. So what is the difference of these batteries? So what have the batteries seen as a type of loads during their service in automotive? And I would like to explain and to show the development process of batteries, and to show you the different types of loads. There may be different, like electrical loads, thermal loads, mechanical loads. And at the end of the presentation, I would like to show what is relevant for the stationary application. So what has to be tested. So what kind of information can we get out of this? So when we look at the environmental conditions, for example, there is a code, international code ISO 16750, so which is the code which is used in automotive industry for electric components. And we see there are many things. So there are, for example, the temperature, we have conditions, chemical loads, and also mechanical loads, and of course electrical loads also. In my presentation, we'll concentrate on the mechanical loads, on the thermal and mechanical loads, less on the electric loads. But of course, at the end, we will see there is always a combination between them. And when we take a look at the different load types, so what can it be for the battery? For the battery, which is, for example, in BMW, it doesn't matter which vehicle. So first of all, we have the road conditions. So it makes a difference. So if you are driving on a good road, or if you are driving on paving stones, for example, so it will be mechanical excitation, will be mechanical vibration, which will be inserted into the vehicle, into the battery, of course. This has to be tested. On the other side, we could have some vibration from if the vehicle is a hybrid vehicle, you can have a vibration from the engine. In case of pure electric vehicle, there will be almost no vibration, so it's high frequency vibration doesn't any impact. Of course, which is very important, this is the charging in discharging of batteries, and so which leads, of course, to aging of batteries. But we'll see another effect, so which is shown here. So we have, I think, very interesting example from Nissan Leaf batteries we had yesterday. And this is the so-called swelling of batteries. So the volume increase during to charge and discharge, and also during calendaric aging of the batteries. So this is quite interesting thing. We have also thermal loads, like thermal elongation. When you have thermal elongation, and it is restricted, and you of course you get mechanical stress into the battery. And we could also have something which is called customer loads. This is maybe not for every battery, but some batteries, maybe as you know, are placed in the trunk compartments for hybrid vehicles. And therefore, so if you put something like beverage crates or stones or something like this, so it can also apply some load on the battery, which has to be taken into account. When we have stationary storage applications, of course, not every loads will be present, like this kind of loads will not be there anymore, but other loads like charge, discharge, thermal loads and so on will still be present. And also the battery has experienced before other types of loads. Therefore it's important. First, at the beginning of the development process, so we need to define what kind of loads, what is the height of the loads, you know. There are different things. So on the right side, you see like standards and regulations, like European, like United Nations regulations. In China, we have regulations and so on. On the left side, also manufacturer's requirements, so like platform strategy and so on. We need to decide. So where the battery will be built in, since manufacturers are developing one battery, and this battery is produced for different cars. Yeah. And of course, we have the customer. So it also different if the vehicle is built, for example, for country with extreme climatic conditions and not so extreme climatic conditions, and so on. So, and this everything. So, okay, now it's working. It's put into development process, and what we do at the beginning, so we do some simulations, like you can see here. You can drive multi-body simulations, drive using the vehicle over bad road, and you can get out of this like accelerations and so on. And this can be later transferred to the battery. On the right side, you see some test tracks. Some test tracks where you do some measurements, and the results of the simulations measurements will be transferred to different load spectra, like like for the noise spectrum, like seen here. This is the acceleration over the frequency. We have also something which is called shock profiles, and this will be tested, everything. So when we do simulation, so you can see here on the left side, this is the vehicle. This is the natural vibration of the vehicle. So it's the first important step before doing any frequency analysis and so on. Drive at which frequency there will be the natural vibration of the vehicle, also the vibration and the displacement in the battery, which is placed underneath the car body. We also simulate the behavior of the battery in the testing. And what we can evaluate after this, we can evaluate the stress distribution, for example, displacement in the battery. We can evaluate stress distribution, for example, in gluing layers and so on. But what is important is the swelling. So this is getting more important right now. So at the beginning of the battery development, everything concentrated more on the electrical behavior. But we have seen that the lifetime of batteries is really depends also on the swelling conditions. And the swelling conditions depend on the type of installation of battery. That means if you put cells into the battery and there is not high stiffness, then the swelling can be working and can be destroying the cell. If you install the same cell into a housing which is more stiff, which is stiffer, then it could be different behavior, completely different behavior. And this is what we are investigating right now. So we have, together with Audi, we have a project where we're investigating swelling behavior for different types of installations. So in I hope that we can obtain results and to see what is the optimum type of installation of the cells to improve the service life. Yeah. So this is a kind of a finite element model what we use for the simulation. This vehicle shown here. So this is a hybrid vehicle. It's a hydrogen vehicle, which was developed by Audi, but it wasn't sold on the market because Audi decided somewhere. So we are not developing hydrogen vehicles anymore because it will not be competitive and so on. I don't know exactly the reason, but other manufacturers are of course producing this. And these vehicles also have battery. Hydrogen vehicles are not driving only using hydrogen, but they need in many cases also a battery. So this is like simulated. What we can get out of this or how it's simulated, we have different levels model. That means that we have a housing, and in the housing we have the individual cell modules. And this is simulated, and where we can determine, for example, the displacements. We can determine the stresses and the elongations and so on, and to find out what is the load on the cell, and how to improve the mechanical behavior. So let's go back to this. So in this example, you can see the natural vibrations of the battery. On the left side, so we have different frequencies, and the interesting thing that if you have frequencies which are in the range of the street excitation from the street, so for example something with 20, 30, 50 hertz, then it will be also excited for vibration. So this is what batteries are seeing in the automotive application. So during the whole service life. Of course, when we take out these batteries, so their excitation will not be there anymore, but it will be kind of a saved history in the battery, and it could be some kind of a damage to the battery. So another example. So what we are doing is, for example, the mechanical stress in bus bars, which are the electrical connectors between the individual modules. So on the left side, you see the measurement. Using length gauges, so to calculate or to measure the deformations on this part, and to prevent failure in service. So the testing of the batteries is usually done. Mechanical testing, it's usually done on electrodynamic shakers, like shown on the left page. This is shown only the mechanical part, but usually when we test the batteries, they will be tested also by electric loads and also by thermal loads. That means that will be simulated all the behavior like it's in real life. Yeah. So what we are doing at our university, at our institute, so to contribute to to understand the different phenomena of battery aging and of swelling and so on. So we do, for example, investigations of cell aging, like shown here, so on different types, different cell chemistry. The picture is shown here for calendaric aging, so under different temperatures, so we can get out information about aging in this case. So next page you see, so this is what I talk about swelling. And we developed a special structure, special testing structure you can see on the right side. So this is for the swelling behavior. So using the structure we can simulate different stiffness of the battery housing. We can apply temperature and we can apply electric loading on the cell during the service. And so we can get out data from this. So this is the aging behavior and the different stiffness of different housings, for example. So this is the which our colleague Daniel Koch will be talking about in our workshop. So he will give you more details about that. I found very interesting paper from colleagues from Daimler, from Mr. Deich. So, and they investigated the swelling behavior, and you can see that the state of health and after a certain period of cycles, battery cycles, is very dependent on the module stiffness. So module stiffness means the stiffness of the battery housing and of the initial compression. So how much pressure you apply at the beginning of the service. So other thing we are doing, so which is also interesting for application in Amazonas, where the air humidity is very high, so is to investigate the water condensation inside of the battery. So there was a special apparatus built. We used many different sensors. So especially if you have active cooling in the battery, so there will be water condensation, or could be water condensation, which could lead to a short circuit, for example, and also to degradation of different materials and so on. So this is we can do here. Okay, so it was a kind of an overview. So I hope I could give you this overview so about the development process and what we see, what is relevant for the second life batteries. It's of course the cell aging, cell swelling from the mechanical point of view, and also the water condensation. And this is what we are trying to do within our project, within our cooperation project. Yeah? Okay, thank you very much for your attention, and so I think there will be a possibility later for questions. Yeah.
Correct. Thank you, Sergey. Later on, we'll invite all speakers from this first morning block up to the stage, and then we'll have a round of questions. But now I'd like to invite Peter Adelman from THUM to talk to us about a BMS for zinc manganese batteries. Peter, can you hear us?
I can hear you. Can you hear me?
Yes. The volume is a bit low, but we are working on that. Would you like to share your screen so we can make sure we can see your slides?
Yes, I can share my screen. One moment.
And please let us know if you hear any echo from our mic here.
So you have to allow me to take the screen, please.
Okay, we're working on that. Can you try again, Peter? Sharing.
Yeah, now I seem to be possible. Thank you very much.
All right, thank you. We can hear you. Your screen's still loading.
So,
just 1 second. We cannot see your slides yet. There you go. Now we can see your slides. We can hear you. You may proceed with your presentation. Thank you.
okay, if you hear me doubled, maybe you have to put yourself on mute. Okay, so first of all, thank you very much for the invitation. Ricardo, thank you for organizing this event, and also my greetings to Pedro and to my colleagues who are with you. So I will give a presentation which is related to that what Emanuele already started to say, but I'm more concentrating on a controller for the zinc manganese battery. I use the multi-stage principle. First again, a few words about storage in general. So if we look on storage for photovoltaic solar energy, we can differentiate between day-night storage. We need sometimes storage to overbridge weather periods, and we would like to have, that would be our dream, a kind of seasonal storage. So far, no commercial seasonal storage is available. There are some tries to bring seasonal storage on the market, but so far it's unfortunately far too expensive to find a commercial solution. So here, this slide should give you a short feeling what kind of capacity is needed for the different kinds of storage. These numbers include some safety. So, for example, for day-night storage, you reserve usually the capacity which is equivalent to 1 day energy consumption in your system. For weather storage, at least here in Germany, we have a lot of bad weather periods and they could be relatively long. We will reserve 6 days. And for seasonal storage, I'm talking here about southern Germany, we need about 70 days of consumption. We have to store about 70 days of energy consumption. So this is about 20 to 25% of the annual energy production. On the spreadsheet below, you can see that the storage demand is pretty much depending also on the location where the system is installed. You are currently in Florianopolis, and you need maybe a little bit more than half of the storage capacity for seasonal storage we would need in southern Germany. But there are some even better places on the world. I'm currently also having a project in Namibia. Namibia have a lot of sunshine, and in Namibia there are nearly no seasonal fluctuations. So 10 days of autonomy would be enough for Namibia. On this presentation, I'm concentrating on seasonal storage. For weather storage, for weather period overbridging, the most economic solution so far is the good old lead acid. The cycle life we need to achieve in a period of 20 years is below 1000, maybe 500. Lead acid is good for that. And for night storage, so far, the best solution would be lithium iron phosphate, so LFP batteries. In a period of 20 years, you may need about 4,000 cycles. But it's possible, if you have the right battery, inexpensive enough, that you can cover 2 or even all 3 of these categories with one storage system. So technically, for example, lithium would be able to cover all 3 categories, but as you can imagine, it would be by far too expensive to use lithium. Our hope is that we can use zinc manganese, at least for seasonal storage and additional weather related storage. So here you can see again the features of zinc manganese batteries. The cycle life is probably not too high, so Emanuele is a bit more optimistic than me, but I already told Emanuele for application 100 cycles, 100 full cycles would be by far enough, even to cover 2 of the storage categories. The zinc manganese batteries may become very inexpensive. I mean, more optimistic than Emanuele at this point, because we see similar cells already on the market at even not very high quantity, below $20 per kilowatt hour. A key feature for application of seasonal storage is low self-discharging. Emanuele already talked about that. But also have some challenges with these batteries. One challenge is that there is a high variation of the voltage between full charge and low charge. And it's related to the low self-discharging. There is no electrochemical process besides the main electrochemical formula. That means there is no self-balancing in the cells. For example, in lead acid batteries, you have the electrolysis, side reaction, and electrolysis help you to balance lead acid batteries. Here in the battery, the other side of the medal of low self-discharging is that you need balancing. These batteries you see on the market, on the right hand side you see kind of battery we are looking a little bit on. It's made for electric fences. It has quite large capacity, and for the applications we are looking for, we will need quite large capacity. So I told already Emanuele that I would like to have batteries with more than 1,000 ampere hours. So how to overcome the problems? I would say a traditional way to overcome the problem is a solution where you have a DC converter at the source side, at the charging source, and you have another DC-DC converter at the load side. And in addition, you will need for this battery also a separated balancer, similar to the balancers we know from lithium-ion batteries. But we have found another approach. It's the so-called multi-stage converter. This multi-stage converter has some nice features. For example, let's say in this easy example, we have the target to form a battery system with a nominal voltage of 5 volt. That would mean, sorry, please excuse, I catch a cold today. The advantage of online presentations is that I can't affect anybody. So here, for example, we are looking on the charging rule, and the charging rule is very simple. We put as many cells in serial connection to come closest to the 5 volt. And we use always the cells which has the lowest voltage. So we are charging the cells which are not yet fully charged, and we charge as many of them to achieve a little bit over 5 volt. And for discharging, we have a different rule. For discharging, we use the strongest cells in the serial connection, and we use as many as of the strongest cells as are necessary to come close to the requested 5 volt. And that means this circuit has quite some advantages. It covers a lot of problems where you may need, in other cases, different electronic circuits. For example, we can do charge control. Very simple. If one cell has achieved the end of charge voltage, we just take it out of the circuit. It will not be charged anymore. We also can do a kind of MPP tracking. We can select the number of cells in a way that we come closest to the MPP voltage. Of course, this is not very fine MPP tracking in this example. It only works in steps, but please understand, I use for this presentation only the example of having 5 cells. If you, for example, in reality form a system with 48 volts, you may have 60 or 80 cells in such a serial connection, and you can do the MPP tracking really fine enough. But you also can adapt your battery system to the load in the same way. To be honest, it is important to know that MPP tracking and adaptation to the load may mean there is a conflict. You may not want to choose the same voltage, so you have to decide what is more important for you, MPP tracking or load adaptation. But this circuit also is able to do the balancing. So you don't need an extra balancer because you just charge one cell after another, and the balancing is coming together with overcharge protection. At a certain point, all cells should be fully charged, and no cell is overcharged. So I already come to my conclusions. Zinc manganese is a very promising candidate for seasonal storage, and if Emanuele works hard and achieve a high number of cycles, we even can cover eventually, or let's say probably, the other 2 categories of storage. a problem of this battery cell is the large difference between the lowest and the highest possible voltage. That makes us trouble in adaptation to the charging source, maybe the solar panel, and also to the load. We need special treatment, otherwise we risk high inefficiencies on the adaptation side. Multi-stage inverter might be a good candidate to fulfill this requirement. The circuit in general is very efficient because it has only low volt MOSFET in the circuit, very low ohmic MOSFET, and in addition the circuit, due to the same reason, is very inexpensive. And one more word to my friends there working on the field of second life of batteries. Due to the fact that this circuit has also the ability to do the balancing, it might be a very good solution for second life batteries, especially for cells which are very different in their capacity. That could be solved. My institute got a patent, or let's say applied for a patent in this field, but I'm happy to share some licenses with people who are interested in that for second life applications. So that's all what I want to tell you. Thank you very much for your attention. I would like to be with you in Florianopolis. Must be a very beautiful place. Maybe one day we have the chance to see each other in person. Thank you very much, and if there are any questions, we can answer them now or later.
Thank you, Peter. We sure look forward to having you here with us in Florianopolis sometime soon. We are leaving the questions for the end of this block, so we have 2 more presentations, and then I'll call you back for the discussion session. Is that all right? Okay.
Okay.
Thank you. So now we're going to hear about the very important topic of the development of measuring device to categorize used cells, which is super important for life batteries. And for that, I'd like to call Ian Haas from TU Ingolstadt.
So, welcome to my topic. Today we heard already interesting presentations about second life batteries, and maybe I can give also an interesting overview, because for second life batteries you must categorize the quality of the batteries, and for this there is a research project Sustain in Germany. I will give you first a quick overview about the institute where I'm working, and overview from me. And then I will go into detail from this project. So, yes, so I'm a research assistant at CARSMA, especially at the CE-Course Institute. It stands for Institute of Electric Connected and Mobility. This institute is part of the THI and is one of the institutes from the THI. I think we'll must change back to the
Okay, so yes, at the CA course we do primarily, we have different teams, for example, battery pack design, or we have also a Car2X group, and I'm working at battery testing in the safety area, for example, for APU series, and later on there will also be pictures of this, because for this sustain project we need use test series, but I explain the details later. We have also two other institutes at the CARSMA, the Institute of Automatic Driving and Institute of Safety and Future Mobility. Yeah, the names are saying they have different targets of research, but my work is especially for the app series you see like here. For the second life, this kind of battery doesn't need second life because it is completely destroyed. The main target for this test was extinguishing and different kind of materials to test what is the best. The cooperation with the firefighters in Ingolstadt. But for the project Sustain, we want to develop a measurement device to categorize second life batteries. And here are the different partners. We are a consortium from 3 companies and 3 universities of applied science. I think yeah, the THI, the University in Aalen, and also the University of Applied Science from Köln. An interesting part is maybe also the company Acurec, because this is a German cycling company, and the measurement device we are planning to develop is one target group is cycling companies. Okay, so but first, okay, what are our interests in this situation? The e-mobility is growing massive in Europe and also in Germany, so there are more and more electric vehicles, and this means also that if there are more and more electric vehicles on the streets, accidents with these vehicles will rise also. And the actual situation is, if, for example, an electric vehicle crashes with a normal car or also electric vehicle, the crash is extreme, so that the whole vehicle go to the cycle process, that the battery pack is going to, for example, Acurec, and they will dismantle the batteries and recycle it completely. But maybe only 50% of the battery pack is really damaged, and the other 50% of the battery cells can use, for example, for a second life. The actual situation is that there is no difference, so they recycle the whole thing. They will also recycle completely functional cells, and therefore the project Sustain was funded because to develop a measurement device to categorize if the cell is useful for a second life, and not like this one, but like a normal cell. And therefore we're working together to achieve this goal. First, we want that this measurement device can work with all different kind of batteries. So not only one battery type from one OEM, because the situation is also that there are no standards. So each car manufacturer built his own battery pack in a moment, or maybe yeah. And yeah, and we want also that we can categorize the quality of the battery. For example, there is an unwritten law. It says that capacity is beyond 80% and the impedance is double double of the impedance, for example, if you compare to a new one, then that should not be used anymore for a traction battery. And therefore, we want to analyze different cells. So this cell we see here on the slide is the cell we're working at a prototype first, so that our prototype can scan this kind. So we started with cylindric cells, but in the end it should be also possible to measure pouch prismatic cells. And yes, one important thing is, for example, the end the time, because if the recycling company needs for one cell 2 hours to analyze the quality of the cell, it is not an interesting situation for them. So to get a better overview, we have here this graph. So we split the project in 2 sides. So first, we want to analyze the under normal test environment, labor situation, the stuff, and then implement it for a really usable test device for normal recycling companies in Germany. So the first thing was, okay, for example, we have in the mid our battery with unknown conditions, and therefore we want different type of cells with, for example, different states of aging or other defects and matches. And then we want to analyze the methods and route all together in a damage catalog. And with this damage catalog, in the end, we want the most informative analysis goes to our measuring device, because that this can, in the end, we quickly decide what are the conditions of the cell. Yeah, so therefore we have this two sides, and in the moment we at the beginning of our project, so we defined our different damages. So, for example, nail penetration damages or internal circuit damages, and wrote this together. And the next step is then to create 3 data pools. So we have the one data pool. These are really cells from the industry. We got them from Accurex, so they are directly from normal electric vehicle, the battery packs that goes to this recycling. And we want to analyze this to see, okay, which damages are there in this kind of cells. And the next data pool is what the HI will create. We will buy new cells. We already did this. We bought new cells, and now we want to imprint damages to them, so that we know, okay, we have this kind of cell, and we know, okay, we did the overcharging. These are the condition of the cell, and then we want to test, okay, is it possible for the device to check and recognize exactly these damages we imprinted in the cell. And the third data pool will be simulations, so that we simulate a cell and then also simulate the error or defects in the cell. And then we have the 3 data pools to create the algorithm for a hopefully good functionally measurement device in the end. So, for example, here are some measurement methods we are thinking about in the moment. No load voltage measurements, pulse measurements, current profile or power profile. Also, we are thinking about ice measurings, but the main problem is that each measuring method needs time, and we want that the measuring device in the end can categorize this cells a little bit quick. So this is one of our main targets to get to decide what are really the important methods for the measuring device to categorize cells, and then to do the tests of the cells. Okay. The next point, also very important, is the validation, and therefore we have the University of Applied Science in Aachen, sorry. It's one of our consortium's partners because they have the labs and the technology to go very deep. For example, computer tomography or X-rays of the cells. So there, when, for example, the THI imprinted an overcharge damage, that the University of Applied Science can analyze this and compare it with the cells we got from Acurec, from the real industry, and also compared with the simulations that the University of Applied Science in Cologne are doing. Okay. In a moment, the slides are... Okay. Yeah. So these are the different steps from our project to develop a functional measurement device in the end. And for example, for me would be, okay. On the next slide would be an overview about the different damages we are talking about. So because with the abuse test series, it is important to imprint the defects and damages to the cells. But during this imprinting process, if the cell burns down, the cell is not anymore valued for our project, because if you burn down cell, it is not good for a second life cycle because it's destroyed. So we must imprint it, the different damages without destroying the cell, and this is the difficulty we will go on to this summer. Yes. So, okay. Maybe I can switch now. Yeah. Okay, here for example have we now the overview of different tests. For example, discharge or high temperature or very a crash. So if you have a crash, we have a deformation of the cell, and a deformation can furthermore for an inner circuit. Inner circuit first furthermore goes to a terminal runaway, and then we have explosion and fire. And we must imprint some edges, but in the end we must get this done without the explosion and fire. Because, yeah, if the cell burns down, this is not more valid for deeper analysis in Aachen. Okay, so thanks for your attention, and hopefully I can give you a short overview about the same project. Thanks.
Thank you, Ian, for your presentation. I'm sure everyone's very anxious and full of questions, but we have one more presentation and then we'll move on to the discussion. I'd like to invite Vincenzo Benetti from Atlas Power to talk about aligning green energy generation, storage, and usage. Vincenzo is also responsible for the second life battery charger that we'll be looking at after or during our break. So he will also talk a little about that at the end of his presentation. Then we'll do questions, and then we'll for the break. All right. Thank you, Vincenzo.
Thank you very much, Marilia. So, good morning, everyone. I would like to start by thanking Professor Ricardo for the opportunity to be presenting to you today, and also to everyone that behind the scenes working to make this day possible. I would like to extend things for everyone that's watching here presently and everyone watching us online. Well, today I would like to share a little bit about our experience at Atlas Power in these three pillars: generation, storage, and usage of green energy. And I would like to go in depth into the storage aspect, the second life batteries. So let me introduce myself. My name is Vincenzo Benetti. I am the CIO of Atlas Power, and today we have here Diogo and Gabriel as well. They are my partners. We are the co-founders of the company. So I would like to start by history about the company to understand what we do and how we get to the point of the project that we are going to see today. It's the carport charger with batteries. So Atlas Power was founded in 2018 with expertise in batteries, solar energy, and electric vehicles. We noticed the market demand for reduced energy costs and decarbonization. So we want to reduce pollutants, still generating energy. And our mission is to accelerate the adoption of smart batteries integrated with clean energy sources, creating viable and sustainable solutions. Our product was in 2018 here in the laboratory photovoltaica. It was a BMS that's the needed to run lithium-ion batteries. And a fun fact, it was aimed to work on a second life battery back then. So we create this equipment to ensure safe operation of batteries and enhance efficiency, as well to have full control over the battery, to get data and act upon the battery, and to customize the hardware as we need for our applications. Afterwards, we create a EMS, that's the step above, is the energy management system. That's a cloud-connected system where we can feed data and we can act upon our devices. Now we can have a fleet of devices to control and to manage in the field. Here we have a picture of what it looks like. And last but not least, that's important for today's presentation, we are currently developing a charger, both 7.4 kilowatt monophasic charger and a 2.2 kilowatt three-phasic AC charger that will have OCPP compatibility, which means that you can have like charge stations in the public. It's a protocol. You need to have a lot of chargers on the field. And these chargers, they will be also integrated to our EMS system to enable some different features, like charging your car using only solar. Because we have the information from the solar, from the batteries, from the grid, we can ensure and talk to the car to make it charge only using renewable energy, only using what the solar is generating right now. So this was the first idea that we had to create the car. This is the main objective of this presentation today. We want to integrate those four things: a battery, an inverter, our solar energy, and a charger. Just to give a brief overview about the other that are not the battery. We have 64 modules on this project, 13.4 kilowatt peak of energy production when they were new. Our hybrid inverter that can both use 8 kilowatts from solar battery independently. And our charger that today we don't have the connection yet, but we are going to change it for the connected one in the future. We have a 7.4 kilowatt monophasic charger that you can set the current. And just to tell a bit more about the batteries that are being used on this project, we're using 2011 Nissan Leaf batteries, and we have a little table here to show what they are used to be and what we have today in terms of battery. So we have the cell that's used inside the battery. They have 125 watt-hour of energy and weight 800 grams. And then they have the gravimetric density of 156 watts per kilogram. Then you take this cell and we put into small modules this little metal encasement, and you put 2 in series and 2 in parallel, and you achieve 500 watt-hours of energy in storage. This module weighs 3.8 kilograms. Now we have the protection for the battery, so it's a little heavier, and we achieve a gravimetric density of 132 watts per kilogram. Then you pick 46 of these small modules and put inside a protection case for the car battery, and you are going to get something like 82 watts per kilograms in gravimetric density that by today's standards is very low, because if you see the 2019 model of the car, you have 62 kilowatt hour energy battery compared to 24 from 2011. It weighs a third more, around 410 kilograms, and it have a energy density, gravimetric density of 151 watts per kilogram. So here, if everything goes right, we're going to see a video of the disassemble of batteries that we're using there. But it's going to happen because maybe it's not open. But fortunately, I know that Aline, that's going to present in the future, is going to show the video. The video is very popular, so you guys are not going to miss it. We're going to come back to the video later. And now, I don't seem to be able to continue. Here. So here are the batteries after taking out the car and putting on the battery pack that we are using on the carport. So we are using 56 modules to S2P. We are using a bit more batteries than it was originally on the car, so we are using 2 cars. We are using a car that 32 modules from one car that we estimate that we have 90% of state charge, and 14 modules from another car that we estimate that have 70% of state charge. The interesting thing from these cars is that they were used in different applications. They were taxis, they were used by police and by universities. So you can clearly see the difference in capacity from one car to another. Then we created 7 towers to create a with 14S, 14 cells in series, and 16 cells in parallel to achieve 53 volts, a low voltage to be safe, and 24 kilowatt hour of energy storage. So we have the same energy storage as the car in 2011, but we are using more modules. Here it's data that we picked up in tests yesterday and this last week that's related to this application, and afterwards we are going to open a link with the live feed of this data, and we're going to go to see the project working live. But just to tap on the challenges using second life batteries, because we don't have the model of the batteries, we try to use the best arrangement possible without too much information. So yesterday we used a 6 kilowatt load to test the system, and that you can partially see on the bottom image. And on the top image, you can check the 14 cells, 14 voltages that we can have in the battery bank. So it clearly shows a picture where some cells are drawing much more than other cells. Some cells are not even, and some cells are getting a very big voltage. So that's what I have for you today. I would like to open the live dashboard so we can check afterwards the project. Here are my contacts. Feel free to ask me anything, to add me or talk to me later on today. And I don't know how, but on the bottom right, I have a link that it's invisible right now. If you want to open it, it's going to go to the live feed. But thank you very much for your attention, and anything, just
Oh, I see it in the bottom now. All right. So now we're going to open for questions. But for that, I would like to invite all of our speakers from this morning's block up here so the audience can see you. So Arn, Emmanuel, Sergey, Peter, online, of course, Ian and Vincenzo. Peter, can you hear us fine? Okay, we cannot hear you, but I can do some lip reading. Amanda, a gente não ouve ele. You're fixing your audio. All right. Can you say something, Peter, just so we can check if we can hear you now?
Yes, I'm unmute. So can you hear me?
Yes, now we can hear you just fine.
Ah, perfect.
And you can see most of our audience now. And we have all the speakers up here. We're going to be sharing this mic for answers, and then we're going to have another mic going out for questions. So if anyone has any questions, you can raise your hand. And someone from our team, please, down here. Someone from our team will come with a mic.
Thank you. I'm Rudy Buehler from Clean Technologies. I have a question about what we heard many times being discussed today, Second Life batteries. And the question is, I see there's not a standard for collecting data from batteries being used first time in cars, for instance. And I see also there's a lot of things going on about how to collect this data in a uniform wise, and to get this in a situation that we can really compare and see what the performance of batteries was, how it is performing now. So I also read about there's a lot of standards going on for this, but the question is this, when will these standards be ready? Will these be available? Because I think they're very important for the second life use of batteries. So that's my question. Thank you.
All right. Anyone want to take that? Perhaps Ian, would you like to take that? Yeah.
Yeah, for example, before the project we did also research about what are the standards for second life batteries, and in the moment this is a situation there are no standards. The market, like Arne also showed, is coming now, is growing now, but in the moment there is also no market for second life batteries. This is coming now, and for example, we also defined in new status, because for us in our project it is not only important, for example, the state of health, because we thought also about a new state, we called it state of usability, because maybe the health of the cell is still good, but there are other kinds that the cell can't use for a second life, and therefore we defined this new one, and we want to publish also in this direction, but in the moment, there is no more standards. Is this Arne, or would somebody else?
I can just underline it. We are looking for strategies for German car manufacturers. They are asking for it, how to bring down the cost for batteries and how to use them longer. And we made up this theoretical framework, and within this theoretical framework there's a clear need to analyze and a clear need to construct them in a certain way. So it's not only important to analyze and to standard it, but to also construct them in a different way, as Sergey also showed, because the way they are constructed will affect also the possibility to use them longer. and Jan is doing a method to analyze them and to also to standardize the analyzation, and then you can use them longer. Yeah.
Just one follow-up question. Sorry. Thank you. The question I have is about, I saw a lot of testing you do in the use of automobiles or cars when they're in original use. The question is, I've never seen any of these batteries, especially simulating and seeing how they perform and what is the damage they take because of vibration and resonance of the metal structure and so forth. I never see batteries being built in cars using sort of bumpers, sort of shock absorbers. The question is, has this ever been considered, or it will never be considered, and any reasons for never to use this? Because, I mean, military equipment normally have this. Everything goes into any sort of military equipment has a lot of bumpers and shock absorbers and so forth. I don't see this being used for lithium batteries. Question is why?
Just a short introduction of mine, and then to Sergey. This is actually the second or third slide I showed. The design philosophy, and we do this together with the University of Aachen. The design philosophy today is doing something for a special purpose and then never thinking about how do you use it in a second life. This is not the way this is planned. This is just, we need a battery for our vehicle, and this just works within our vehicle, and then we don't care anymore. And this is also, we visit the IFSCI, where they try to do, rebuild cars that use normal engines, electric engines, and they try to contact German companies and say, so we need help, and the German companies won't help because they are not interested. Someone here, you were, yeah, they just are not interested because our philosophy is just we build this thing for the first life and we do it perfect for the first life, and the second life we don't care because no one has thought, and this is new strategy approach, no one has thought about using something longer. It's just one time and it's perfect, and using this the long scale, this is not planned. And now I give to Sergey.
Okay, thank you, Arne. Concerning the, I think it's a very interesting question, and I had to think about it because usually when we are designing batteries, we have to achieve a very stiff structure, and when we have a very stiff structure, the battery is very robust. So if the cells are inside of a cell module, for example, then it has to be very stiff. And the only thing we have to do is, of course, for the whole battery, that we have to see not to get resonance problems like high vibration levels and so on. When this is achieved, so my experience that the mechanical vibrations and shocks and stuff like this is not very critical to lithium-ion batteries. So this is more the static load is more critical, like coming from swelling and so on, much more critical than the vibration. In the development stage of batteries, there are different levels. So we start with testing individual cells. Then we start with testing of cell modules, and even at the end we start with testing of batteries. And the levels of vibration for individual cells are much more higher, so they are 3-4 times higher. And even using these levels, so there is, when we have a good structure and a good design, so we have not seen many damage to this. So, yeah. Therefore, I would say from this technical point of view, this kind of structure and cell chemistry it works properly. Yeah.
I have a question from the audience. O Silvio Salas asked for Emmanuel, and I think maybe Peter can complement. Are zinc-manganese O2I batteries already available for sale in Europe and South America? And what is the round-trip efficiency?
So thank you very much for the question. So at the moment it's still in early testing phase, this type of stationary batteries. So they are showing like use cases. For commercialization, I think still will take a while. And for round-trip efficiency, it depends a lot on the depth of discharge to use this battery. So at the moment, at the lab scale, we have a value around 70 to 80% round-trip efficiency, but we believe that by reducing a lot the ohmic losses and improving design, we can go to 90% or beyond.
Peter? Okay. I have some questions from Robel Obara. I will do one and then we switch around and then maybe I come back. He says that he loved the presentation from Jan Haas. And the first question is, able to correlate electrical test measurements with specific aging mechanisms, especially lithium dendrites, and how? Dendrites, sorry. Are you able to correlate electrical test measurements with specific aging mechanisms, especially lithium dendrites, and how?
So if you are able to detect the dendrites inside the cells during the aging process, yeah, but this is not you can detect it, but not with our planned measurement device, because then you must go deep inside the cell. For example, the university in Aalen can this, but this is the time thing again. If you want to analyze it in detail, you need more time, and we want a product in the end that is usable for the normal industry companies in this area. And yeah, so no, it's not planned at the moment. I'd say.
Okay, I have a round of questions to one question to each one of you. So to Arne, you are worried about designing product for a later use in Second Life or even further. But isn't this a conflict of interest for the industry? They want to sell everything new all the time, all new and again. So they don't want you to have. No, just a second. I will go around the whole questions, and then you can think more.
Okay.
And then you expect to. You mentioned about the expectation to export batteries from Germany to Brazil in Second Life. Do you know if that is possible due to regular issues related to exporting junk trash? Okay, this is a question to you. Emanuele, you just told us that your round-trip efficiency is 70 to 80, expecting to go higher. And how many cycles would you like to have in your battery before you go to the market? I understood well that if you contain swelling, you will have a better product. So if you make your case stiffer, you will be able to have a battery that is lasting longer? Is that the question? Can we find your product in the market? If we want to start a project here in Brazil, even if it's at the prototype scale, would we be able to have this multi-stage concept that you have shown us here in equipment ready to go? Jan, what are your targets in terms of time and energy use? Because Arne has also told us that it doesn't pay in Germany to do sorting. And here we are very much looking to make sorting happen. So what is the target of your research? And finally, Vincenzo, do we have a product that will be able to go to the market for high power? Because I think the main interesting part of your concept is that you don't need an upgrade in infrastructure. For 7 kilowatts, I can tie that up to the house, and I don't even need the batteries. But if I want to go to 22 or even bigger, higher powers for fast charging, so how are you prepared to tackle that issue? Because that, I think, is the most important one. Thank you. So we start with Arne.
Yeah, thank you, Ricardo. Thank you for your question, and it was a quite long question, so expect a quite long answer. Well, I got to begin at the beginning, because the strategic approach was, and the whole thing was, from the German industry, if you want to make something cheap and you do it especially with expensive parts like batteries. The battery in the electric car is a very expensive part, and now to gain momentum and to scale up and bring the electric cars to the market, you need to make the most expensive part, like the engine or battery. You need to make it cheap. And how do you make it cheap? An old approach, just doing it a lot, just scaling up. But the problem with it works with engine, with everything, but it doesn't work with batteries, because there you got two limited resources. The one is that you don't get the material. As we all know, lithium is something, the price went up, and even if you change the material, the same thing will happen. If you have a big demand, it's hard to get. That's the one point. The other point is that you are in a beginning market, and it was a fast change, so the car manufacturers don't have the plans to build batteries in a large scale. You just have to buy them or have to build plants. Both of it is expensive, and so you can scale up by buying a lot or producing a lot, because you can't. Now is this how you can drop the price in the usage, and the only approach to do it with batteries is use them longer. Of course, you got the conflict there that you have to do more engineering at the beginning, and also have to find a network of users, and this was I was talking about in my second slide with this governing structure. You have to find a set of partners. You have to find someone that will use it after the first use and the second use, and they have to commit to use it as in the state of production, because they only will get it in 4 years or 7 years or somewhat, and this is quite a risk. So of course you have got to pay for all these risks, and this is why using a battery for a longer time, of course, is more expensive in the first place to build it, yes, but in the long run the usage costs will drop. And then I will answer your second question concerning having garbage export to. We don't consider, if you do it like this, we don't consider it anymore as garbage, but as a working part. And this is the very important point where we need Sergey and we need Jan and we need all of you. Then we analyze these batteries, and we don't consider them as they are done in their first life and now we do a second, but they are done in one part of their life and now comes the second, and they are still working, and the still working part, and this is just switched in place or location, and this will then not be exporting garbage, but exporting working parts. And also, as you know, the large manufacturers are standardizing their cells, and they use them with every car in the world they will produce. So the parts will be interchangeable, even in size and capacity, and this will just be a part and not any battery that has been used and now it's something. But this is the plan. This is the strategy. Okay, I'm now giving to the next person. Thank you. Yeah.
So if I recall, your question is how many cycles we want to achieve before going to commercialization. So our approach now, please correct me if I say something wrong, but since one of our aim is this seasonal storage, at the beginning we cannot wait 100 years to get 100 cycles and say, okay, now we are ready. So the idea now is to get it commercialized as fast as possible, to showcase what our battery is capable of, and have several generation. So let's say a first generation, for instance, for this seasonal storage, where having 10, 20 cycles would be a lot of time. And then second generation would be the 100, 200 cycles, where we also target the other type of application, but we want to commercialization as fast as possible. Thank you.
Okay. So the question concerning the cell swelling is also very interesting, and I have seen different results so in the past. The first result, so when I worked at Audi, we have performed such experiments, and that for specific cell chemistry for design, it was better to have the construction as stiff. The worst thing you can do is without having any restrictions. So this is the first thing. But I have also seen experiments right shortly that were showing that the stiffness of the housing should be somewhere in between. So it's shouldn't be zero, but it shouldn't be as stiff as possible also. So it seems to be dependent on the chemistry, on the design. This, in fact, this is a very research question. It's not completely understood yet. And the other thing we have to think about, even if you say, even if it would be a solution to have very high stiffness, that would mean that you need a very stiff housing, and in the vehicle to having a very stiff would mean much more weight and much more cost. So therefore it should. Therefore we have running application right now, Audi, where we would like to investigate exactly this question. So yeah.
No, I did not get your question. Repeat it, please, loudly.
Yes, can you hear me? You can
now
hear
I
me.
can hear you better.
Okay, the question is, can we this stage principle applied in a device already? Can we, if you have test this principle here in one of our projects, be able to find it in the market or either a prototype?
The multi-stage principle is already on the market, but for different applications. You find it already built in inverters. The original principle, the very basic principle, was invented in Fraunhofer Institute in Germany in the 80s, and it was used voltage of solar modules in a way that it becomes wave. That was the original application, and you find already such applications on the market. That's what we are doing specifically. I started to develop that. We have some steps in the lab. And Ricardo, since we have I'm happy to discuss to you later what could be done in Brazil. I'm happy to share some secrets with you, and let's see what we can do together.
Thank you very much. Excellent. So next time we see each other, I expect to bring something home in my suitcase.
Yeah, but please, then don't come before it.
It's Ian. Ian's turn.
Yeah, I talked time and never mentioned it directly time. Moment we are in the pre-phase from the project, and our target is to get characterize the important in 20 minutes, because the main problem is the ice measurement. Because if you want to do this, then you need time. You must go through the frequency, and this is the reason why we are not 100% sure what are in the end really the important methods to characterize. And we are in the pre-phase of this. And yeah, so the 20 minutes are our target. And also, this is the first prototype. We want to go further, or there are plans, not first to go to models, to directly model levels, so not only each cell, then you can do it faster if you can do more cells at one time. And yeah, but in the moment 20 minutes are the target.
So I would like to divide the question in two answers. I would like to answer by DC charging and AC charging. So for AC charging, we have everything that we need to scale up. So if you are saying that you need more power and more capacity in order to have 22 kilowatt AC chargers, it's possible right now. And the magic happens when you have these 10 chargers and you have only access to 30 kilowatts or 20 kilowatts grid, and you don't have to remake all of your infrastructure to have the ability to charge all the cars. So you put more batteries, more inverters, more chargers, and you're going to be able to ramp up the capacity and the charging capability. For DC charger, it's possible right now as well. We don't have our DC charger, but it's going to be less effective than what we would like. We are planning to develop our own DC charger, but it's going to tap directly to the battery. Right now, we are going to have the battery, have the inverter, and pick up a commercial DC charger to ramp up the charging time for a single charger. So everything is possible, but to not go through this efficient trip, it's worse. We are planning in the future to develop our own DC charger.
Perfect. Anyone from the audience has questions? We probably have time for one more. If not, Aline has some questions from the online chat, and maybe we can do one more before we move on.
Sorry, Rafael, I'll let Ian know the questions afterwards and he answers in the chat for you. So congratulations, Gabriela sent congratulations for the event and presentations. I have a question for Professor Emmanuel and Professor Peter regarding the battery. Do you have a TRL estimation for this technology?
Yep.
Readiness level.
So a few years ago we were really at TRL 2. Now I am confident to say we are at a level of 4/5, but this is more or less where we are right now. And now we are getting a new project, a German project of several millions to bring it further, this technology, and bring it to at least a 2 level higher, we hope, and as soon as faster to commercialization.
Thank you very much.
All right, so if we have any remaining questions on the chat, we're gonna have our presenters answer that directly on the YouTube chat. Now, I'll let Vincenzo steal a couple minutes of our coffee break to show his dashboard for his battery, and then we're all gonna go outside and see the battery with our own eyes. So thank you, all of our presenters for answering all of our questions. And Vincenzo, you have 2 minutes because everyone's hungry.
Okay, no problem. I just want to show very briefly the dashboard that we have. We have like live information from the cardboard that we're going to see right now. I'm going to be stealing your coffee break time. I know that's very important. But just to add one small thing, as you can see, I didn't show you, and there's a lot of information, but our state of charge is 0. Why it's 0? Because we don't have this information. It's set to 0 because all the batteries, they are second life batteries. We don't have the monitoring, and you didn't use the equipment to check all the batteries in order to know each module, how the battery is looking like today. So I hope that after this event, we are going to have all this data. It's as accessible. It's public. I would like to see if we can create an online information for state of charge and state of health with the knowledge that we are generating here today. Oh, okay. So if we're going to go outside, have the coffee break. And here, where you are going to see a lot of cars parked with a solar roof, it's going to be to the left. We are going to see a gray battery on the floor. That's where the pilot is running for the charger and the carport.
All right, so everyone gets to go outside and see the e-mobility charger, have some food. We'll try to be back here at 11:20 to move on with the rest of the day. Olá pessoal, espero que todos tenham tido a oportunidade. I hope everyone had the opportunity to go check out the e-mobility charger using life batteries during our break. We are now going to proceed with the rest of our presentations for this extended morning that we're having today. So right now we are going to hear from Fabian Schweikart from Global Power Unit about a battery standard leading to big performance. Fabian, can you hear us?
Yes, hello, I can hear you quite well.
Awesome, and we can hear you quite well, and we can see your slides, so I think we're all set. Thank you.
Amazing. Perfect. Shall I start?
Yes, please.
Yeah, hello everybody, and first of all, also a big thank you for letting us be part today in the opportunity to present Parsi, our company, and the concepts we are currently working on. My name, as mentioned, is Fabian Schweikart from Parsi Group, and maybe a bit different to the content before. My following content will be not deeply technically today. It is, it should just be a first impression about our company and our concept. Yeah, today's topic, the Global Power Unit, a battery standard leading big performance. In a couple seconds, I will refer to the picture why we did choose that, but before we dive into the content, a quick introduction about us, the Parsi Group. Who is Parsi? The Parsi Group is a growing organization dedicated to the development of sustainable energy solutions, mainly in mobility and logistics infrastructure. Besides a small team in the background, it is mainly Franz Ringelhahn as founder and idea provider, as well as myself that are working on the business development of the company. Yeah, we are sitting in Germany and myself in the Netherlands, so it's placed in Europe. For the beginning, I want to circle back to the image we already saw, because this represents the origin of Parsi Group and our ideas. Ringelhahn, our founder, participated about 3 years ago as a volunteer at Engineers Without Borders, mainly to learn about the work and the situations on the ground in Africa. And during this time, it became really clear how unreliable the supply and the infrastructure down there is. Especially, vehicles carrying medicines, food, or other items get quite often stuck on the unpaved roads. As well as we see on the picture, the gasoline-powered SUVs even fail quite often to reach their final destination. This situation can be reduced or even solved by changing the way of transporting goods. During this time, it was also the time when several of the concepts and the ideas of Parsi Group were born, as well as one of the Global Power Unit. But what is the idea behind the Global Power Unit? Our primary goal is to develop a global standard for compact, portable energy storage by, in the first step, using second life batteries. We take here for illustration this 9-volt battery and combine it with a worldwide used and probably well-known Euro pellet, theoretically. And the aim of these two elements is to create a universal measure that simplifies the use as well as the construction and also the exchange of these batteries. Outcome and our concept is a new global standard, the Global Power Unit. This open source battery storage solutions with the dimensions of a Euro pellet should create a quite big flexibility. The technologies in common are currently undergoing a major transformation, as probably all of you know, like technologically wise, capacity wise. Big changes are happening. But with a standard housing and basic measurements, there are almost no limits to the areas of applications. The technology itself in the inside is not quite relevant for the user and the customers. In the end, he just should receive the power and the capacity he needs. Also with an advantage to check and organize all these batteries online. The issue of higher efficiency coupled with lower heat loss also benefits our concept. And this new standard opens up completely flexible and new possibilities in use. The topic flexibility we already know. We do know that from consumer areas, because many of power tool manufacturers show us already today scenarios where it is possible. One battery, 100+ use cases, different power tools with different cases. It is quite flexible, still combined with one problem, and this is called brand standards today. Flexibility has been quite limited to products only to a single brand. Means almost every manufacturer you also see here currently operates with its own battery solution. So there is no universal product used. And this is only just a small selection of brands on the market. Thinking about our global power unit, we have already quite some use cases and see the flexibility. On here, possibilities range from use as an external charging station for electric cars to relieve existing power grids or to provide needed additional capacity. So on the right top side, you see the basic shape of the global power unit, and just turned and added with charging cables. It is an external charging station immediately. Further use cases can be, so on the right top side, you do see an example for an automated.
I hope everyone had the opportunity to check out the e-mobility charger using life batteries during our break. We're now going to proceed with the rest of our presentations for this.
Can you still hear me?
Today. Yes, sorry, Fabian. I think we had a bit of a technical problem here. From Global Power Unit about a battery. If it was just one moment, we're fixing that.
Yes. Can hear you quite well.
Awesome, and we can hear you quite well, and we can. Can you check if you have your YouTube running with the presentations?
Yes. Do you still hear me? Because I do hear something in the back.
Yes, we can hear you, but we can also hear some echo from YouTube recording. But it seems to be gone now. Okay, I think we're good to proceed. I'm sorry about that.
Okay, then I will go on. On the top right side, you do see like an example for an automated guided vehicle, mainly used in the logistics sector. But mobility solutions in passenger transport are also possible. On the left bottom side, you see like a prototype already from Audi, as well as other vehicles such as forklifts or vans. A battery standard leading big performance. In addition, the possibilities also extend to on-site applications, either in remote areas without direct power connections, or as a substitute storage source to bridge downtimes or cover energy peaks. RC Group is a growing organization. The two examples on the top refer to developing countries such as Africa and therefore the remote locations, or another concept of ours on the bottom, a solar-powered hall for food cultivation or indoor farming. As well as myself, that are working on the business development of the company. The biggest advantages of our global power unit will be an extreme high efficiency of the energy use by close to 93%, as well as the multifunctional use thanks to the waterproofness, as you will see in a minute. The inductive charging of global power unit makes it even more robust in several use cases. But beside the basic concept, we go a few steps further. How can we also use these solutions to bring about the process change in general mobility? So we do not look at a battery storage system itself from Second Life batteries, but also at its use and the implementation of global electric mobility solutions, as well as we see a revolution of transportation. The concept herefore is an outlook, so-called the global move. This is a vehicle with a base of 7.45 meters in length, a weight of about 40 tons with a loading weight of 30 tons. This vehicle is multifunctional use for either freight transport with containers or passenger transport. Some facts here. This concept car is driven and powered by 6 of our global power units and 24 top-wheel engines with a power of 15 kilowatt each. In the first step, this combination gives strength and power for even unpaved terrain. The lifting height is up to 20 centimeters. With a worldwide, I mentioned that this could also be used in passenger transport. And you do see here a flexible space that opens up new possibilities in autonomous passenger transport. And it could be quite easily connected to the base of our electric truck. And our concept, not to forget, is the basic charging process. The global power unit. How can that look like? The pure charging process can be minimized with this solution. So-called loading bays allow the global power units to be exchanged for types of vehicles in roughly around 5 minutes.
Fabio, sorry to interrupt. We're still getting a bit of a delayed audio over here. Could you double check if you don't have any tabs on your computer open with the presentation, perhaps?
I can check if you give me a second. Yes. The technology itself in the site is not quite relevant for the user and the customer. Can you still hear me?
Hi, Fabian. Yes, we can hear you, and we stopped hearing that background noise that we had earlier. We cannot see your presentation.
At the moment, I cannot hear you.
Fabian,
I'll just try to share my screen again.
All right. Were you able to check if you had any tabs open that perhaps had some audio going on? we don't have your video and we don't have your presentation up right now, just so you know. Okay, we see your screen right now.
Share my screen. Just let me know if you do see something.
Yes, yes, we see your slide now.
Can you also hear me? Can you give me maybe a thumbs up quickly?
As we can hear you, we cannot see your video, but we can hear you fine and we can see your slide, if you'd like to proceed.
Okay, perfect.
Now we can see you as well.
Shall I quickly do the couple slides before, or shall we just go on from here?
I think you can go from here. It's clear.
Okay.
Okay.
Then I do quickly go on with the charging process. Yeah, with this so-called bay, this allows the global power units and different kind of vehicles to exchange a global power unit within 5 minutes. As you can see here, the different kinds of vehicles can drive into the loading bays, and fully automated, the battery units will be switched. Our next goal is, as mentioned, the revolution of transportation, water-wise and land-wise. As I told before, our concept of the global power unit is waterproof, and this in the following steps means the true revolution of transportation. Firstly, the revolution on land, because the global move is roadworthy, but also on water. Means whether somewhere in the Amazonas or its side arms, as well as in urban regions such as Cologne in Germany, partly lower water depths. So this solution is definitely globally emission-free and decentralized. Looking at the outcome and the chances to use this, we watched the global shipping routes, ocean-wide and river-wide, and it is quite clear the extent of use, how it may look like. Especially open waters, it is powered by wind, sun, waves. But step by step, the development of the global power unit would give us countless opportunities to rethink mobility, change of transportation in general, and still work sustainable. So I hope even with the circumstance of sound, you got like a feeling what we wanted to transport and what the goal is of our idea. And thank you very much for your time. Many thanks from Europe, and let's evolve sustainability together.
Thank you, Fabian. I think we were able to overcome a bit of a technical problem during your presentation, but it was very clear. We're going to wait to do questions at the end of the session, if that's all right. That will be around 6:20 p.m. in Germany. All right. So now to move on with our presentations, I would like to invite to the stage Lucas Nascimento, our researcher here at Photovoltaica UFSC, and he will be talking about the role of batteries in decarbonization of the Amazon today.
Obrigado, Maria. Good morning, all. Amanda. Also, if you could just reduce a little bit my mic. Thanks. So the goal of my talk today is to give a perspective of the role of systems in the Amazon energy transition. So in Brazil, the electricity, 9.4% of that is basically supplied by our SIN, the Interconnected National System. But as you see, or not, let me back here. You see, north of Brazil are not connected to the interconnected system. So most of people is living there, and this represents around 3 million persons. This is less than 1% from our total population that is not supplied by our interconnected system. They are supplied by our isolated system. So not all people from the north, this is a small part, but an important part. All these people basically are supplied through mini-grids. And right now, we have operating there around 212 mini-grids. The majority of them, 80% of the total energy from these places, are basically supplied by diesel gensets. If we have a close overlook on these grids, we could have basically cities from 100 persons up to 100,000. So the scale varies. And this could be the typical genset group for a small city, and this could be a typical genset for a large-scale city. But most of them, the majority of these places, if we have a look in the medium power demand from such cities, we see that in the range of 400 kilowatts. So this is the typical system that basically is supplying energy for places. This represents around 1,500 megawatt year of energy. And then we have the question, okay, how we change that? How we can go for a smooth energy transition in the Amazon? Could be wind. So you see wind potential in the north region, except here in northeast Roraima, in the border with Venezuela, we don't have a so strong wind availability there. So wind, probably not. If we look for biomass, so for the 212 locations that I mentioned, in 42 of them, if we look for biomass waste, so basically this is waste from agricultural process, crops, and also waste from wood chopping. And also this is certified wood. So in 42 of these places, around 20% of mini grids, we have biomass waste to supply 100% from the load in these places. So it's a good percentage for sure, but this doesn't cover the whole Amazon. And then we have solar. Good potential, modularity, flexibility. So solar for sure is a good option, as well as other sources. But we don't have a silver bullet to solve all the problems from the Amazon. So we don't have a one-size-fits-all solution. But I don't use all stars anymore. But I think all stars, they match with any outfit. Doesn't matter if you are attending a meeting, a class, whatever. All stars is a good option for all those as solar energy. I don't think that solar energy is the solution for the Amazon, but for sure it will be part of the solution. It will be part of the solution, whatever the place. For that, unfortunately, we know that solar is not a dispatchable source, and in place with solar, we have a storage system. So this is one of the systems that we have operating here in Brazil, just a showcase, showing that for this place, this is Bahia, this is not north, this is not northeast of the country, but for this place we have a rural system, isolation also, is not part from the CISOL, but here just showing that for such case, in this system we have 100% solar penetration. The only two sources, the only source here is solar. And together with storage, you could have 100% of energy supply here. So this is the typical solution that we are looking for in Northeast. Well, 100% of renewable penetration is possible, for sure. The sky is the limit. But the bottom of the pocket also. This is expensive. So when we look in a typical PPA agreement that the companies which are running these mini-grids have for such places, we see that if you have a short PPA, you cannot have such strong renewable penetration because you don't have the time for the amortization of the equipment. But if you have a long-term PPA, then probably you have a high possibility of renewable penetration because you have the time to pay the equipment. So it's not clear yet what will be the move from the government in the next auction. But we think that probably we could have for next auctions at least a renewable penetration of 60% for such places. So this means that we have a solar system and a storage system that could supply 60% from those places, and diesel or other source will supply the other 40. If we have a look in the possible combinations of storage and solar, and this is basically showing how we are seeing the PV capacity, the PV power against storage capacity, we see that for higher penetrations, we need at least 1.5 gigawatt of solar. This is a really impressive market. Could be a really impressive market. And looking for storage, our goal here, this means 2,700 megawatt hour of storage. Also, these are utility scale projects. But not all of those people that I mentioned, the 0.6% of Brazilian population, they live near a mini-grid. Some people are far away. So it's too expensive to bring the grid to there. And then the typical solution is to build an individual solar system. And this is more light for the Amazon project. It's pretty much the same program as Light for All, Luz para Todos. But this is specifically for the Amazon. And here you have a few PV modules and a small storage system, up to 5 kilowatt hour. If we have overlook in the 2 years, 2021 and 2022, more than 50,000 systems were installed here in Brazil. So this is a 150 megawatt hour capacity just in the distributed off-grid systems. So look on this perspective. That's my final comments and challenge that I would like to share with the colleagues. First, for the small systems, the Mais Luz para Amazônia, more light for the Amazon, so they are individual systems. The logistics is not that hard. For the utility scale mini-grids, a utility scale storage system doesn't fall off the sky in the middle of the Amazon. How you bring such container solutions for such places? So logistics need to be think. Also, who will give the support for installation, commissioning, operation of such systems? We need to have trained local support there. Do we have? We don't have it. Not yet. Also, we have here in Brazil companies, and we also have in the market the availability of such size in the market to attend this probable scenario. These will be supplied with first life batteries, or also could be second life option. I don't know, a lot of questions. Finish here and share with you to be probably in the end of our session. So finish from here. Thanks a lot by your attention.
Thank you, Lucas. Now I would like to call to the stage Joaquim Gonçalves from IFSC. He'll be talking about electrothermal simulation of EV batteries under driving conditions.
Thank you for the nice introduction. What's the pointer here? Pointer? No pointer. Let's continue our workshop here. And hi to everybody. Good morning. And firstly, I would thank Professor Ricardo Hutter for organizing and supporting and inviting us for this workshop here in Photovoltaic Laboratory. Okay. Then I will talk about the electrothermal simulation of electric battery in a vehicle under driving condition. Let's understand this. Put a car on a chassis dynamometer, for example, to take the data and then using fundamental model to adjust it by then take the parameters of the car, the inertia, and the resistance of the movement. So then we will take a little bit about the battery, overviewing lithium-ion batteries, and then the electrothermal model and the dynamic model that I developed here, and then the chassis dynamometer that was used to adjust the model, and then we have at the end some simulation results also. Then this is in fact used like to design or to analyze a vehicle that are using electrical motor and battery to see the autonomy, for example, and in my case, I'm interested in seeing how is the thermal behavior of the batteries in the car. Okay, then just looking very first in the lithium ion, there is lithium metallic floating on oil. It's a kind of a light metal. There it is in vacuum because it is very reactive, okay? Then it is some models of cells, and in the right side we can see a pack, and then an application, for example, in a boat. That's something that goes from lithium to cells, packs, and then the application. And at the middle you see the round plot a kind of analysis of the density of energy and power of several energy storage technologies. Then we can see here some of the behavior in terms of voltage. There in a comparison of lead-acid batteries in with some lithium-ion model, and then the effect of temperature, for example, and of the current there. And here in this graph, we see the open circuit voltage, and then when you put current, then you have some drop because of ohmic resistance, and then we to have the activation, polarization drop, voltage, and also the concentration polarization. That means the diffusion. It's necessary to transport ions in the battery. Mostly this is kind of a fundamental, that is the understanding of how the batteries of a lithium-ion battery works there, okay? And then we can go straight from the developed model, electrothermal one. Then we just put like a balance of energy, in this case considering the thermal variation of the energy, generation heat, and the heat transfer. Put those equations in terms of their parameters, we developed like a equation, of order differential equation, then we can get a solution, analytical one, if we have like some period of constant current. Then we have this kind of analytical solution that can be used in the case of step-by-step when we have constant current in that moment. This can be for few seconds or maybe minutes of constant current. Then we can go step-by-step in the simulations. Then those steps can be just few seconds or maybe minutes or so, depend on the variation of the current on the battery, okay? This is kind of the step-by-step that we can march using that solution together in a numerical method, okay? Then we have the thermodynamic model for now. But we need to put the vehicle on that model. That means we need to go to the dynamic of the vehicle, to go to the force at the beginning, then to convert this in the current that is the source of the energy in the electrical motor, okay? Then we go through the dynamics doing the balance of force. Let's say we have a moment when we are accelerating the car, we are delivering power to the wheels, and another moment we may be regenerating. We are braking the car. That is the flow of energy, okay? Then this may be done with a strategy of regeneration. It was done here just as an example by considering the currents. If the current is higher than 0, this means that we are driving the car or we are braking the car by analyzing the force that's in the model, okay? After that, we have to have a relation between the voltage of the pack during the running. This is done, take the data from dynamometers from Argonne National Laboratory. They have a vast, with a few cars, different model, and took a Nissan Leaf 2013, the data, and this is show when was a process of charging the battery during around 2.5 hours. The red points were the delta, and the blue one is the first trial of the adjusting this to get a curve to put it in the model, okay? This is the first part of the adjustment. Next, the complete model is put together, and then all the parameters present in the model was adjusted. This was the model for the force, the dynamometer. This was measured and was given in the database. The current also at the end was the temperature was the thermometer that was put together. Putting all this together, we have in them a model that can be used to simulate or to analyze or to design application. We have a vehicle with a pack. Then I go on showing some comparison between, let's say, the battery state of charge from the data, directly from the current of the data, from the calculated, from the simulation. Okay, then we can see these curves are almost the same or very well done. Then showing that the model has a very good representation of the data. This is in the side of the graph, I have the distance or the kilometers was and the autonomy of the car, and here the consumed energy is the same almost of the state of charge presented directly in terms of energy. Okay, then this was the global results, but the important one that I was seeking at the beginning is the behavior of the temperature of the pack, the cells in the pack, during the running time. This is almost 2.5 hours, and the measured and the simulated temperature I did quite well for now. And then some simulations led with the constant speed, that means zero acceleration. Then we had some heating, then almost stabilized temperatures, and also with some fluctuation in the speed. And it was accelerating and braking in a sinusoidal behavior, and then the temperatures also get quite a similar behavior at some time, and also the state of charge is in green. It was dropping, and with some behavior like a wave, is acceleration and braking process altogether, all right? And then I may go to a next step that we are doing now with the student, Murilo Stein, is a graduate student that will be in Ingolstadt in September and October. Then you'll be studying there and doing some period with them there. And now we are writing a paper for the campaign here in Florianopolis in December. Then we will put this model together with some improvements. The improvements is in the voltage curve. This we have done a new adjustment with the voltage at the output of the terminal is function of state of charge plus two terms. One is the temperature, variation of temperature in the battery, and the other is about current. No? Before I have done just this part. First part was a straight line here, not straight, but a continuous line. Now it's beginning to take some consideration about the current and temperature in the battery. And next one, it will be to put like an equivalent circuit model instead of just putting statistics and just coefficients. In fact, we will be taking some coefficients that represents also constants of time in capacitor and resistance in this kind of circuit. No, this represents that the cell has a source of voltage like in open circuit. This is the electrochemical voltage, and then some resistors and capacitors that represent the behavior of the variation with current and temperature involved in this. This is, in fact, the point we are now. And mostly, we are in this point. Next steps, improving the model and applying this with the data from a dynamometer. Is a car that is a converted car, is a Celta converted with another student. I don't know if he's here. No, because he was trying to even bring Celta here to show to us, but we have him with us in our group, and to put this in a dynamometer, probably with Marcelo Van Dressen, that we will be talking with the meter of Instituto Federal of Santa Catarina, okay? Then, here are my contacts, and I'm professor in the Federal Institute of Santa Catarina in the area of the refrigeration and climatization. Thank you to everybody.
All right. Thank you, Joaquim. Now I'd like to invite up here Marcelo Van Dressen to talk about the conversion of combustion engines to electric traction. Thank you.
Okay, first of all, thank you for inviting for this meeting. And first of all, we are working the same way, but in different business, or in the same business in different ways. Because you are all talking about second life of batteries, and we're working with second life for cars. So it's a kind of different approach to a problem that I believe in Brazil we're not yet facing, which is what to do with second life batteries of automobiles, because we don't have those, or at least so many that becomes available for tests. The Brazilian fleet's about 11 years old, so now we might have a few hundred electrical cars that are reaching that age, hybrid ones, but I believe we are gonna take those electrical vehicles further than 6, 8, maybe 16 years, even if they don't perform as like 80, 70, 50, 60 something. When they still work, I believe they are still running on the road, and no one is going to disassemble cars at first. So let's start another problem. Let's start converting cars that are no longer used or are old, and then the engine is failing, and the greatest source of pollution and maintenance is the engine. So you have to change oil, timing belt, spark plugs, clutches, everything. So we're facing a way to change that situation. Get a car like it's 3 or 5 years old. We change the engine, take it off. So we take most of the problems off. We keep the problems that we do have in an electrical car. We have to change the tires, shock absorber, rings, brake pads, and we're doing that like on a financed way. Let's see. Oh. Should go further. Right. Okay, now it goes. So the job that we got is to develop a conversion system. It's not just a conversion of the cars, but it's a system, how you can do that, to convert a few electric cars. And the job was set, and we had to do 4 different conversions. And we chose cars that we are using actually in Brazil. Brazilian people see them a lot, see these cars a lot. And 2 from Fiat and 2 from Renault. And who likes notice the cars that are running on the streets, you see that the mail company Correios here in Brazil are using Fiorino, Estrada, and also Speed or Mobi from Fiat, other cars, small cars to transport boxes. So it's a high volume, but low weight that's being transported on these cars. The first car that we have converted, and we say it's a mule, because we work it a lot. The people that were visiting yesterday or the day before yesterday, they went to the lab. I was installing an electric column, driving column on this Fiorino. And we have a difference between all the cars, because we have to do 2 cars that are cargo, basically cargo, 2-seaters. And we are also converting 2 quids, also as 2-seaters. They are 5-seaters, but we are using them as 2-seaters. But we are always changing imported powertrain with a big battery, local powertrain with a big battery. And the other ones, imported powertrain with small battery, local powertrain with a small battery. So So crisscross the situations and then it goes. The Fiorino was at first 1.4 engine. It would run on benzene, on gasoline and alcohol, but it was actually running as natural gas. It was natural gas installed on it. And the first two cars that I'm going to talk about, the Fiorino and the Strada, they are cars that were, let's say, used in crime, and so they got the cars donated, so the cars are for free and they get a second chance to live as a research car. So at first point we had to do this one, and on the way it was the first one, it was the hard one. They didn't have any videos on YouTube about converting Fiorino, and the videos that you get usually are converting Volkswagen Beetle, Volkswagen Buzz, Porsche, Maserati, older cars. In Brazil we have a law, and the newer cars from 2012 on, so 11 years from the fleet, they already have ABS and airbags installed. So it's one problem that we must keep that working, and it's not so easy. It's quite easy to put an engine on a Volkswagen old car, because there's no technology, no lean, no CAN, no nothing, just wires. You can make it analogic. And so we had to do that as a, so we have to keep that in mind, that ABS and airbags I don't want to test, but the ABS it's still working for sure. The computer checks the airbags, they are there. So the first point we had to select the engine, the inverter that comes with the engine, the batteries, and the big question is nobody tells you how much power do you need, what do you do. Usually you have a 10:1 ratio, RPM, on the cars that you buy, on a Leaf, on a, where you buy it's 10:1 usually, 9 something, 10 something, on the ratio on the gearbox. We didn't know if the engine was going to be enough. This one is a Chinese engine, so we decided to keep the gearbox of the car. It has 5 speeds, so we wouldn't miss that much to get off. So we are using now the 3rd gear, so we have 2 lower gears and 2 upper gears. If the engine was underdimensioned, we would know, but we would still keep the conversion using the other gear car. So the first big problem we had, the first milestone, was to select the engine and the inverter that comes along, and the size of the battery. The first car we did, the Fiorino, it's easy because we just put the box on the trunk and it keeps working in. The batteries are safe and they're separated from the driver, and it's quite easy to do. On the way, one of the other milestones, we have to put a charger, we have to put like a computer to drive it so that we can make the changes that we need, the torque on the other elements that we have in the car, as the vacuum pump, water pump. We still have water refrigerator on these engines, and the charger, and also in the we have to use water, so we have to turn on a fan and so on. And so that was the first car. A lot of different components to install on these cars, and so problems to face. Air conditioning was one of the problems that we had, so we got a lot of other elements. And when we got ready, we went to the second car. This one has a VAG engine. It's built here in Santa Catarina. It's a local content engine, also the same package of batteries. All the batteries that we used are imported. This one was, the second car was not hard, but yet not so easy. It's a different car. In this one, also the same equipments were installed. We had a better pack of batteries. We built, for the first 2 cars, we built the whole pack of batteries. So we have to design and manufacture, install the BMS and everything. And that's the final result, the power bank on the back, and we already started on the 3rd car. The 3rd car, well, it's 3rd car, but it's different. It was not the same philosophy. In this one, we made a hybrid, imported powertrain, 2 engines on the wheels, and a small imported battery. It's a complete pack, closed pack. So we have a lot of communication problems. Now everything runs on CAN or LAN or other communication. It's not that open. It's not easy to get hold of it. This is how it looks from underneath. We just had to make another axle, but we did it. And now we are working on the last car, the fourth car. It's a quid. We are installing the content engine on the gearbox, a smaller engine. It's gonna work. We have a lot of partners. We hope we still got some chances to make new projects. And where are we going? We've learned on the battery pack, the engines, the installation. We don't use the clutch anymore, how we do the coupling from the engine to the gearbox. And now we are planning to teach what we learned. So the big milestone that we have now, we have enough knowledge to teach other people how to do this, how to convert cars, newer cars, and let's say we can have other sources of second life batteries in the future. We are planning another project to try on other kinds of cars, especially bigger ones, medium pickups, medium trucks. So that's our phase. We are in the future to do other conversions and also to teach what we've learned. That's it. Thank you.
Thank you, Marcelo. And now to talk about the challenges of applications of second life batteries, we have Aline Kirsten here. She's a researcher here at Photovoltaica UFSC and also the president of the Brazilian branch of the International Solar Energy Association.
Thank you. Thank you, Marilia, for this kind introduction, and thank you all for coming. I'm talking about the challenges of the applications of second life batteries, telling you a little bit about the applications that we did here at the lab that you're going to be able to see yourselves afterwards. So, as Marilia said, I'm Aline, and let's start. So, quick overview. We are here at the north of the island, the Sapiens Park, a technological park, where we're going to be able to walk a little bit. And when we came here to start our lab that revolves around solar energy, we, from the beginning, realized that storage systems and also electrical vehicles would walk together with solar systems. And especially because we are quite far from the main campus of UFSC, so 25 kilometers especially, we came to a big project some years ago that is this electric bus that we have here in the corner. So you will also be able to meet it, to see it for yourselves. But he's here, and he used to do 5 times a day this way until the central campus of our lab. Is 50 kilometers way and return, and it's totally moved by solar energy because our lab provides all the energy that it can. And the energy is not over the bus, but the energy that is being generated here, our roofs, are enough, and there's a lot left to supply all the energy needs. So in the sum of generation and consuming of the year, it fits well. However, even in sunny days, because our bus goes and comes back 5 days a day to UFSC and then has to be recharged, the last time of the day that it's being recharged, it's still taking a lot of energy from the grid and expensive energy, because it's the time that the energy is most expensive and it's the time where there's no solar energy. So less charging is quite bad for the grid and also like for environment and everything. So we did some simulations to see how a storage system would go to fix this problem. And for starters, the photovoltaic systems reduces the peak during the day, most of the peaks. At the end of the day, there is this peak. This is a simulation for 1 week. And when we put a storage system, this big peak is removed. So we said, okay, we have to have that, a storage system here. But we have a lot of batteries being discharged right now because of the increase of electrical vehicles. That's mainly why we are here to discuss the use of the second life batteries. And so why not to use these second life batteries to reach the full cycle? And the batteries are being discharged for electrical vehicles are being used for charging back these vehicles and eliminates the big impact that they can have on the grid. So we started some years ago studying that, starting with a project, a partnership with NISA. They had some NISA Leafs running around São Paulo and Rio de Janeiro for some years, especially with taxi drivers. And when the project did that, they had to discharge these batteries, and we received 12 of them, and now we are doing tests on them, and also doing some applications to see what would be the best applications for the second life batteries. One idea to use these batteries, so this is how the batteries go out of the car, is to use them closed like this. The problem about it is first the information that the car manufacturers don't want to provide us, that is the communication and everything about this vehicle. That's a hard challenge to get all this information and to be able to install this directly to an inverter or anything of power conversion that we. And also, this model of Leaf hadn't any type of ventilation inside of the spec. So there is some type of inequality of heat inside the spec, and because of that, inequality of degradation between the cells. And all the cells inside of the spec are in series, so it's hard to continue the application with some of them more degraded than others. That's why we dismantled the systems. And that's the video that Vincenzo wanted to show you before, because Atlas Power and us started together this partnership with NISA, and that's so Vincenzo is there, and also Lucas from our team are dismantling a pack from electrical vehicle from this NISA Leaf. So inside the pack there are 48 of these modules, of these cans, and inside of these cans there are 4 cells, 2 in series and 2 in parallel. So we unmount them and we try to sort them out and to test them to see how we can use them again. And here are some pictures also from Atlas. So these cables here are their first tries on BMSs for these systems. And here are some pictures of us testing the batteries for their application. So we characterize them, the batteries, to sort them and choose which batteries will go further. And here are some results. This is the results from our thesis from one of our master students, Mateus. Some tests that he made saw some interesting results. First, this is some tests of capacity measurements of different cars. So we have here 8 cars, 7, and the variability of capacity inside the same car is huge. Also, among the cars are huge. So how can we connect them together if a lot of batteries inside of them are so different? So in this second graph, you can see like we are comparing the first batteries in a series, the last one. So 1, 2, 3, and for 6, for 7, for 8. And you can see there is a huge difference of capacity. So there is a variability between the cars, and within the same car. So that's a big challenge. Mostly with capacity measurements, but means that we charge the batteries of 1/3 of their capacity. So and that takes a lot of time. So at least 3 hours to charge and 3 discharge. So it's a whole day work for. And we are trying to do some more tests to try to correlate tests that can be more fast to analyze this battery them to the capacity that it's a long procedure. So first, also Mateus did some measurements of resistance. So that's a good correlation. So when there's the internal resistance is a good call for their estimated state. However, some studies, that's not from us, it's from a paper that was published on the matter, that when there is this degradation, when the battery degrades really fastly, and that it's not necessarily predictable by this internal resistance. Another student is working on that as well. I will give it on that. There is Lucas, our bachelor thesis on that, and now is continuing on master. And Teus and Lucas are going to also be capacitated on that. Lucas is trying to use more complex models to batteries, and also do another test such as pulse charge and discharge to try to model the batteries and try to create them as well with the capacity to see if we have a quick estimation of the health of these batteries. So these are some of the tests that we are. And then after testing it, we are doing with it. So one of the applications that you're going to see is illumination poles. So that's the most reliable application that we have, because we have batteries that are in parallel, so they are easy to control. Powering of the batteries is quite reliable. Balance, because they are in parallel, so it's easier. And we have this like easily reproducible, put everywhere for these illumination poles. And we can see here a graph depending on the irradiation that of each day, some less hours of light during the night, but it's a big impact because at 3 in the morning there is no one here, so it's fine. And also, we can use the same kind of pole. Not working, sorry. The same pole to illuminate with a similar equipment used in refrigerators. So we have this project with another institute here of UFSC that has small refrigerators, DC, and we could assemble these batteries, second life batteries, with this same structure, really similar. And these refrigerators are really useful for applications in CISOL, for example, but also to carry vaccines that we just realized it's really important to have like mobility for them, and they have to be refrigerated. So that's another great application. And here we have some graphs of their operating. So the line in yellow are the state of charge of them. So they get a bit discharged during the day, but it's well enough, like these 3 batteries used is well enough for using the refrigerator. And the last application, we also a little bit larger scale application for the second life batteries. So we are going to meet that today as well. The storage systems that we have for 100 kilowatt hour of second life batteries. That's a project that we have with ENGIE, where we had this container with first and second life batteries. So the second life batteries are in the same container. So the first life are these ones, and the second life are the right ones. And we have them all together. And the first life batteries, they have a lot of warranty specifications. So to have a lot of climatization and limits for them. So we have a big energy expenditure on that to keep everything dry and cold. So that's a challenge. And if we did an analysis that's not for our storage system, is for one that is similar that we at a 1 megawatt hour storage system that it consumes in one day with the battery of almost 180 kilowatt hour only for keeping the container on, only to keeping the HVAC on. So this kind of like climatization is a big problem, and it's still like a big challenge, especially in Brazil, where we have high humidity, high temperatures. You're going to meet, some of you are going to Manaus, you see that. And also here in the south, we have cold weather as well. So we have to keep it also hot in sometimes of the year. And for that, the round trip efficiency will go down. And for the second life battery, we don't have so much issue of climatization because the batteries were an electric vehicle without no kind of climate conditions. So here they are in much better conditions than that. But we did this application. We put 105 of these little boxes in series, of this module in series. So there are 2 series of 105 in parallel. So we have these 2 racks of batteries. And we use a BMS of Lithium, is an American company. And we use this in the same setup of the first life batteries, so the same PCS and the same connections, only changing the batteries themselves for first or second life. Sorry. I think some slides are missing. Okay, no. Okay, I'll just keep talking. Meanwhile, can you put my slides back again? I thought I went to the end, but I didn't. This slide is wrong. I'm sorry. And for the capacity, don't be shocked with the numbers. They are important, but I have a reason for that. So the batteries that went to the connection had kind of like 60% or even or less, depending on them, before going to there. So first life and second life, each one of them had 100 kilowatt hour of capacity, but the second life had already like 60% of their original capacity. And we did some measurements to measure the capacity, and we already have some losses for the round trip efficiency. So first life is 70% of round trip efficiency because of all these losses of climatization. But still, the second life has another types of challenges. So we cannot take out the 60% of capacity of these batteries, because when we put all of them in series, all of them have different degradations. We can try to sort them out, but when we put them all together, difference and imbalances will be a big part of their energy losses. And also, like the limits of equipment, all of that are important. So we expected 48% in relation to nominal capacity, because it was the losses versus the second life that was 60%. We could reach only 33%. So we have a bigger loss than because of these factors. So factors are them, the limitation by the equipment. So PCS and MS have limits, and the voltage of them take part on the limitation of their power, the internal resistance and the imbalance between them. So when a battery is more degraded than the others, their lower limit voltage will be reached first than the others, and that will stop the whole series. And also for the upper limit, when the battery is more degraded, the upper voltage limit will be reached before the others, and that will also take a part, and all the bank will be. So these are big issues, and we have how to improve that. To have better BMS systems that can balance them better, and also better sorting and qualification procedures that all we are talking today, so we can improve these challenges that we have. So take out messages. So we have great potential for on and off application of Second Life batteries, but the proper sorting of modules to better use this capacity of Second Life batteries and avoid imbalances between cells is very important. The lack of history and user information of these batteries is still a challenge and can improve this kind of balancing. And the compatibility of commercially and available PCS and BMS is also something that we have to face and face as a challenge for this implementation, but still it's a great promising, and we have to continue looking for it and using these applications. So that's it. Thank you very much for your attention.
Thank you, Aline. Unfortunately, Mr. Nam Truong is not going to be able to join us. He was here in our program to talk about extended battery life, but due to personal reasons, he won't be able to join. So we're just going to move on to the next presentation. So I'd like to call to the stage Pascal from THUM. He'll be talking about funding opportunities for projects.
Thank you. Yes, hello everyone. Thank you for welcoming me in Brazil. Thank you for Photovoltaica for hosting this workshop. I'm here through the project of E2 Brazil. It's a cooperation between GIZ and IEEE. We are working this program fostering investments and innovation in the theme of battery technology in Brazil. And my presentation focuses on unlocking funding opportunities for the projects that we will develop through the program of E2 Brazil. And with the introduction out of the way, I would say, show me the money. Yes. Okay, the funding I looked for will focus on the following 5 projects. We have health management of battery systems for Second Life. Here is Professor Ricardo Rüters. He is involved in that project, also universities. We have lead acid and lithium iron phosphate hybrid battery projects. We have solar thermal heat storage in thermal storage in solar home systems. We have a design of a solar grade lead acid battery, and also Emanuele Marini, you heard him before, talking about rechargeable zinc manganese batteries. What you see for all of these 5 different projects in common is they all focus on the storage of energy and in particular batteries. And you can see here listed a nice assortment of Brazilian and German companies, universities and institutions that will work together on these projects through a partnership between Germany and Brazil, which is also the core point of the E2 Brazil project to foster cooperation between German and Brazilian companies, universities and institutions. A quick overview of what I will do today. I will quickly talk about some institutions that provide funding which you can approach. Also, I already looked for some possible programs. I will talk about them in a sort of funding matrix I created. Then I will talk about what the EU can offer, also more in detail the application process that the EU program you have to go through. Afterwards, I will show you some projects already received funding to show you what kind of projects get accepted, and also as a foreshadowing for the projects that hopefully also will receive funding throughout. And then to finish off, a small recap to bring it all together. So to start off, sources for funding, which institutions and who can you approach? There's of course German ministries you can approach. The BMWK, that stands for the German Ministry for Economics and Climate Protection. It was with our new government we got recently renewed, So that's why also climate protection. Also another big one is this one, BMBF, the Ministry for Education and Science. So the German ministries, they are definitely one option which you can approach for funding. It depends on the project, but they have, so to say, lots of different programs to offer regarding education, science projects where you want to apply technology. Also, don't forget the EU. That one's also a big station to apply for funding. They have two main themes. First is their funding and tender opportunities website where you can apply for calls, more on that later. And the other part is the specific programs called Global Europe and LIFE. And lastly, also another important partner you can approach are, of course, corporate institutions. So for example, Siemens or Humboldt are just two to mention. They really focus on usually education, or if you are looking for scholarships or maybe exchange programs. So depending on what you are looking for in your project, in your corporation, you need to approach these different institutions. Okay, first up I will start with if you want to apply for funding at the German institutes, how does it work? So the BMWK, on their website, they host kind of a search engine for specifically for funding programs. You go to the website, you can search for fitting programs, you can apply many filters. So, for example, is your program, are you looking for funding for university, for company? You can select the theme you want and also the type of funding you want. Do you want a loan? Do you want a grant? And so on. After you found a program, then you can inspect the program, read through it, check if it's applicable for your specific program. After you read it, you think to yourself, yeah, that program fits, we should apply. Then usually they're also on the website listed always the person or institution rather, or company you need to contact. I will also talk a bit later about a specific program. Yeah, you contact them, the party usually send in a first draft of your project. And afterwards, if they either say, no, sorry, we won't go any further with that, or maybe they more likely case will accept you, and then you can start the formal application process where you file a formal application for a program, very detailed. Here, this slide I included, it's a wall of text, intimidated. It's just to show a quick overview of possible funding programs by the BMWK. You can always see the name of the program, what type of finance it is. Then lastly, which German ministry actually is responsible for providing the funding. You can see we like acronyms. And then then also the eligible parties that can apply. As a company you can always apply, and certain programs then are suitable for universities and research institutes. And lastly, you can see which institution or company is then responsible, which you need to contact. You can see it varies quite a lot. Maybe some of those contacts are already familiar. You can see PricewaterhouseCoopers, financial institution, and also a few others. But I think you will be able to access the slides afterwards, so enough on that one. And here I want to talk about a bit more about these programs have to offer. Again, the name, type of funding, and then here you can see the funding volume. Usually if you are a company, you can get around 50% of your costs, sometimes up to a certain cap funded. As a university, you get 100%. When available, I also put the funding time frame. You can see a month, 12 months or a year for project funding, others a lot longer. And then here in the scope, I wrote what each program focuses on. You can see quite different. let's say a program that's focused on agricultural, you could still apply with battery programs, because for maybe fences, for remote sensing, looking after your crops, maybe something possible. And there again, as a company, every program is available. Universities only some. How does it work? Now one program in detail that's on the BMW website. The program is called Projects in Research and Innovation Cooperation with Latin America and the Caribbean. Quite a mouthful. The issue of that program is the BMBF, so Ministry for Education and Science. And the contact person is the DLR Projektträger. It's a German Air and Space Association. So how you do it? You apply on the EC Online portal. You can send your project draft. You first send in your project draft to the DLR. For this program, universities, institutes are eligible to apply. As a company, you need to wait for a call for funding. And after, as I said, the project draft was accepted, and send in your formal grant application. What you need for that, very important, letter of intent of the different partners, written memorandum of understanding, and some more. Very important with these programs, always read the guidelines, what you need to send in. Also, watch out for deadlines. Certain programs you need to send in before a deadline. And lastly, have some patience. It will take up to a year from getting accepted to receiving funding. Okay, with the EU, there's 3 big pillars. There's Erasmus+, that one's focused on international mobility, education, and Green Deal. So looking for scholarships, looking for exchanges, maybe organizing workshops. That's where you want to go. Global Europe, that one's more focused on the environment and climate change, digitalization, sustainable growth, and also with the program LIFE. This one is now in the iteration of 2021 to 2027. It focuses on circular economy, nature and biodiversity, and clean energy transition. So you can see the theme of all green technologies, sustainability. It's a theme of the European Union, what it has to offer. For the European Union, very important, there's the applying for the EU grants and tenders. They have a website called Funding Tender Opportunities Single Electronic Data Interchange Area. In this is an excerpt from their website. If you later get the presentation, if you click on the phone, that's a link to the website. And then how do you apply for these calls? So first you find a suitable call where you can propose your project on the website. You find project partners. In this case, it's already done. Then you create an EU account. Afterwards, you register an organization, and then you can submit your grant proposal. All the important steps are all on the website, written in great detail. So don't worry. It's, if you read through it, you will be able to apply, even with all the paperwork. And then here, I wanted to show you what the EU funding and tenders looks. For example, here we see some tenders that's with purple, or focused on solar in the Lebanon, PV systems, and climate control for greenhouses, but the outreach program between the EU and Brazil. And it looks like here that this one is a grant, also focused on electricity and renewable energy. And you can see the program for Africa, the Caribbean, and Pacific. The budget for that one, for that grant, is 25 million. It then gets distributed among the various projects. So that's what these grants and tenders typically look like. And then to finish off the presentation, towards the end I wanted to present some projects that are already receiving funding from the EU. The first one is the development and operation of a green energy community in the port of Montreal. That's a project in Spain, where they want to create an off-grid seaport. So seaport, cargo ships and so on, they want to make it off-grid capable. And for that they will install a 4 megawatt PV system and use 1.55 megawatt hours of battery storage. In the picture you can see all the partners involved in that project. Funding for the project is more than 3 million euros. And yeah, and another one is airport sustainability life battery storage. The way it's written, that's how the program name is officially written on the EU website. And that one is an airport with a solar and battery system. They want to use 10 megawatt hours of second life batteries together with 30 megawatt of PV system to make the airport more renewably powered, and funding for that also around 3 million euros. And largely another interesting program is this long title, large scale vehicle system with integrated stationary storage, harnessing EV batteries and a fast response to deliver grid services currently provided by highly polluting gas plants. So in the title also included a nice project description. And this program is for vehicle to grid as capacity reserve. So here we plan to have 30.8 megawatts in power available, provided by 280 bidirectional chargers and using Fiat 500 electric vehicles to buffer the grid, and when they are connected, act as a sort of gas peaker plant to support it during high demand. Funding for that is 1.6 million euros. I chose these projects in particular because they all focus batteries, solar, and even second life batteries fitting for programs that we are talking in the project E2 Brazil. And then to recap my presentation, my presentation is as an overview of funding, so to show you which institutions you can approach to give you make the first step for you already, because when I looked for funding, it was quite overwhelming. Where do you look, especially for projects that involve companies, universities in Germany and in Brazil, so EU country, non-EU country. But the good thing is that Germany and Brazil, they have long-standing historical relationships, so it should be possible. For each program, maybe a project, maybe a funding program you could approach. I wrote it down here, looked at it and thought it looks quite fitting for each project. Also with the EU programs, lead acid and lithium iron phosphate hybrid batteries, live, and so on. I wrote it as a sort of guide, maybe for first stop for all the people working on these different projects, which stations you might want to approach first. And with that, I want to thank you for listening. I want to thank you for organizing workshop, for allowing me to be present here today, all the way from Germany, and this topic. If you've got any questions or want some help looking for funding, the IEEE and Institute and I are happy to help. Here are my contacts. Feel free to contact me, and afterwards at the lunch or later we can talk and ask some questions. One last thing, I included all the important links in the presentation. So if that gets distributed, here are all the important links where you can already look at the different funding institutions and programs, so don't have to start from scratch. Thank you.
Thank you, Pascal. That's very helpful. All right, so now we're gonna have our last presentation for the second block of presentation. And then after that, we're gonna do questions, and then we're gonna have two other quick talks from Brazilian representatives about other ways of getting funding here in Brazil as well. But for now, I'd like to invite Professor Inga Stadler from TerraCon to talk about maximizing grid utilization and ecological footprint of e-car batteries.
Very much. So hello and welcome also from my side. I would like to thank Ricardo for inviting me here, and also would like to thank Pedro for supporting my trip to Florianopolis. And when I first was invited to this event, I thought, oh, I cannot contribute to that research of second life batteries. And so I decided to divide my presentation because I remembered I had a master student group working on life cycle assessment or the ecological footprint of batteries in e-cars containing second life batteries. And then I would like to talk a bit about the project I love to talk, and that is one of our latest research projects that has to do with charging a lot of electric vehicles in existing grid infrastructure. So, what was my motivation for this student project we have had? And that was always the reports on media that electric battery vehicles are a bad thing. They are bad for environment. Some have even written they're even worse than diesel cars or combustion engine cars on gasoline. But on the other hand, when you have a battery in your house to operate with a PV system, it's always a positive thing. But it's the same batteries from the chemistry point of view, cell chemistry, that are in a house or in a car. And so that was the motivation to look for a different way, because a battery in a car can do more than only drive the car, because the car is almost standing typically in Europe 23 hours a day and only driving 1 hour. So when it's connected to a plug, it could do much more. So for example, it could balance vehicle grid. We can do grid services with it, or we can substitute a battery at home when we do vehicle at home applications. And also we can take into account second life batteries, because in all those studies only new batteries are investigated. And also recycling might be used. And what is really taken into account that we are in the moment in a transition phase. So all those studies take into account we produce the batteries with a high coal-powered electricity power plants. And so that was the start for this motivation. And we did not really make our own ecological footprint calculation. We used other studies that have done a lot of those work. Most are still coming to that battery cars are better than diesel and gasoline cars, but some are very close together. And that was the basis where we built up on our methodology. And what we already see when we take all those existing studies and look to the emission factor of the electricity or energy used to produce the batteries, we see also when we look what is the emission of the e-car per kilometer driven, it strongly depends on which electricity mix those batteries are used. And as most assume the batteries are produced in China with a high coal electricity power fraction, that is clear that then also the emissions of the batteries are quite high. So what we try to approach is a quite simple approach. So it had been said at the beginning of the life the capacity is 1, and at a certain fraction B we stop driving the car, but then using the battery as a second life application, and at a certain capacity loss of A we stop using the battery and maybe bringing it then to a recycling approach. And also, maybe not really correct, we assume that the capacity is decreasing linearly to 0, but it is at least an approach. And then what is the final result of the project that we have gotten? And again, we did it emission per kilometer driven. Using here the different lines is for different applications. So the yellow, the blue one is the standard case where we still have the batteries produced with the actual Chinese electricity mix, going then down to the yellow one, 100% renewable electricity for production. And what is the horizontal graph here? The horizontal graph shows how much the car battery is used for vehicle-to-grid application. So 0 would mean it is not used for vehicle-to-grid applications, and that is then more or less the standard case of all the other studies had been taken into account. And 1 would mean somebody buys a car, never is driving, and only is connecting it to the grid. So depending, the reality is for sure something in between. And then we see that the emissions from here maybe 30 gram per kilometer driven can go down to almost 20, or when we use renewable electricity, that is even getting much better. Why? For renewable electricity, it's even getting worse. That is not the absolute values, but we always take that relation to kilometers driven, and when you not drive anymore or only drive a little, for sure the rest of the car has also the ecological footprint, and therefore this line even increases here a bit. And when we then add a second life, so that only taken into account the first life, when we look to the car battery, that also is then the battery first life is considered to be taken as a grid application in a second life, then we see that the footprint even decreases further. That is only one example that I would like to present here to justify to be here in your workshop. Then I would like to talk about our latest European research project. It's the Progresses one. And again, I would start with the motivation. And again, we have articles in the German press. And maybe the best one here quite often, it says, e-cars, when everybody charges the same time, we get a problem, we have a grid collapse then. First of all, I would like to say we never have the situation when everybody comes at home the same time, because we don't have streets, everybody can come the same time. And I think nobody experienced everybody's coming home the same time, you go to the street, you don't see car anymore. Everybody's now home charging, so it's impossible. But nevertheless, when we do nothing, we could get the overload of the grid, that's clear. And that was the motivation for our research project Progresses. It was led by the Infineon company, and especially the work packages we work on. We did mainly together with Devolo company, a company that is quite advanced in doing power line communication on the grid. And so our aim was that we have a problem in the distribution grid with information. In the transmission grids, we know excellently what happens there, the power flows, the currents, the active, the reactive power, the voltages, everything monitored. But when we come to the distribution grid level, in rare cases, we know the transformer load, but quite often even the transformer load is not monitored online. And definitely nothing is monitored what happens in the lines in distribution grids. So that is the problem where the grid operator then needs to think, okay, I only allow those cars to charge. In the worst case, I still can guarantee that no line is loaded and that the voltage levels are always in the boundaries, that I do not have problems with the applications, appliances connected to my grid. And that is a very sharp restriction. At the same time, we know the average transformer load of a distribution grid in Germany is something between 10 and 20%, meaning we have enormous capabilities to charge cars there. But maybe in some hours we have a problem, but we don't know when these hours are. And that was then the start of this project. So we want to charge more battery-driven electric vehicles, less overload. Therefore, we want to have an optimization algorithm to coordinate the battery electric vehicle charging. We need to have knowledge about the grid topology and the grid state is required. And then we can apply the optimization algorithms. And so we started with this principle that we now have applied for patents for. We received in January the patent from the United States. The Europeans still are investigating whether it's okay to get a patent on this idea. So what we are using is the smart meter gateway, where we have the information from counters as we have smart counters applied in a household. And then the first thing would be either we get from the grid operator the topology of the grid, admittance matrix, for example, or we have the grid topology estimation. And that was the first step with which we started. So when we do not have this data, we have a grid, a simple grid like here, for example, but we have not everywhere e-cars and measurements. But we need to know how does the grid look like. We only know we have a few charging stations, not where they are and not how it looks like. And then we can do by many tests. For example, we can imagine we just do here with the charger a step in power to increase the charging power by 10 kilowatt. And then we look to the response on the other charging station. What is happening with the current, what is happening with the voltage drop here and in all other power stations. And when we do that many times, the matrix like that, and see there are two parts are not connected to each other, and that is then, one is this line, the other one is this line of the low voltage grid. And so we can more or less reconstruct how the grid looks like, and in the meantime we are also possible to get the impedances in between the house quite accurate. And the second thing is then we need to know what is the actual grid state, so the state estimation. And the problem is we need to do that with a limited number of information, because at the moment not everybody has a charging station providing us the information, and therefore we go for a simplification, or we go for a worst case estimation of the grid, but we are sure, always on the sure side of our estimation. So we assume now we have a typical road with 17 houses, but we only have 1, 2, 3, 4 cars, or 4 measurement stations where we know power, cosine, phi, current, voltage. And therefore, what do we do with the other 14 or 13 that we do not have information? So therefore, we go in algorithms and look for a reduction to do the worst case estimation. So we just throw all them out that we do not have the knowledge about. We only have here the last one, because that's the most critical one according to the voltage. And we need here an additional one to estimate the line load here at the beginning of the line that might be critical. And then we just some worst case calculation. And I just want to show one example when we have to estimate what is the voltage drop here. So we know the voltage here, we know the voltage here. We do not know what happens in between 5 dot and 6 dot. There might be 10 other houses. We assume what would be the worst case, and the voltage could look like that, it could like that, or it could like that. We don't know. But the worst thing would be when all the voltage drop here that we know exactly, because that's measured, would result only from a current that's here. And that is then our worst case estimation. And when we know that, we can assume that then the current that we can calculate here minus the one that we know that happens here would then go completely to the end of the line. Then we have the worst case estimation for the voltage drop at the end of the line that needs to keep in the assured limits. And our ideas are for the estimation of the highest currents close to the transformer load and the line close to the transformer due to the what not go into deep that. And when we now have the state that we have, then we can go into our grid line optimizer, that when we know here are so many cars with state of charges and they need to be completely charged or to charge to a certain state of charge, then we can go into the optimizing algorithm, and therefore I just go for some, only that you see the impedances and how we call the currents for the households and electric vehicles and so on. And then we just have the optimization algorithm that for sure we would like to have a maximization of all the currents going to the battery electric vehicles. And our restrictions are just that what the grid operator needs to assure to the customers, that we have in all nodes of the grid that we have the voltage that must always be larger than the minimum voltage so the nominal voltage plus minus 10%. And all this, we need to look that the current line is smaller, like the maximum current allowed in a line, and also the maximum current must be lower than the maximum transformer load is allowed to be. And that is what we built up in our laboratory. So we built up artificial houses. This is one house. We simulate just by a very old lead-acid battery that we got for free somewhere. Then we operate here our household that can be negative or positive, also simulating a PV system, for example, feeding to the grid. And so in this rack here, we see 6 households that we have simulated with the batteries. Here we have the grid monitoring then, and that we have real grid. We have put almost a meter of cables that we also find in the roads in our laboratory. And then what we see in the next and last slide, I think, is here we can connect different configurations, so we can always build new grid topologies and testing our algorithms whether it can identify how the grid is like and doing then the management. And that is now just finishing the project. We also build to attract now industry going for us the next steps for commercialization. We have built with students a communication box. You already see it's an old tablet computer that we integrated here. It's not really nice to sell, but finally here you can enter then when you would like to start, with which SoC you would like to start, or how many kilometers you need to have for the next trip, and the optimization is planning in this local grid operation of the charging process, always assuring the grid is not overloaded. And so thank you very much for your attention.
Thank you, Professor Ingo. So now I would like to invite all of our speakers to come up here. Also, I would like to make sure that Fabian can hear us. He's still with us, Amanda? So we can do our questions and discussion session. All right. Okay, I think that's all of us. And Gustavo will have the mic. And perhaps Danielle, can you check on the online questions? Oh, Aline has online questions. She can do multitasking. Okay, so maybe we'll start with an online question then, so you guys can warm up.
So, Rafael Obara, considering both electrical and non-electrical measurements, what are the most promising quick measures for estimating the state of health of Second Life batteries? And I believe it's for me. I don't know if anyone can jump in, but also I think Jan Hack can jump in again, because it's but for our insights, like those, for our measurements mostly do electrical measurements and verification, visual verifications to see the health of it in a safety vision. The internal resistance can give you a general thought on the state of health, but I said there are some circumstances where, depending on the SoC of the battery, and also if it's too close to the end of their life, that it's not precise, but it's kind of an easy test. Like everyone can do it. It's only turn on and turn off and measure the voltage, and you can have some insight of it. But you have to have some comparison mean to have like other types of battery and have compare that. I don't know if anyone can jump in and answer that as well. And Jan do you have any thoughts on it's just because it's kind of your presentation as well. Rafael asked, what are the quickest, like electrical or non-electrical method to measure second life batteries and have a sense of the state of health of it?
Quickest
yeah.
test. Yeah, I would say that, so for to check of the health of the system of a cell, I would say a normal capacity measurement. So, or, sorry, I didn't get exactly what you.
Yeah, like a quick measurement to have the state of health of the battery.
Yeah, you can't discharge you have the battery and discharge at the normal level. One important thing is if you work with cells, the difficulty is if you don't know what kind of cell is, then you don't know, okay, you don't have the data sheet, and then you don't have the stats. For example, you don't want a deep discharge, but with a deeply discharge you damage the cell. So in the best case, if you have all the specs, then you can work easily with the cells, because okay, you know, normal charge level is 2.4 volts, and if you go lower, it can be damaging the cell. But yeah, for that the difficulty is if you don't have data sheets for the cells. Okay.
Totally agree. Thank you for
Hopefully.
jumping in.
Okay.
And I have another question for here. For you, actually, yeah. Like, when I can have you a new car, my car converted, and how much does it cost?
Well, it depends on the price of your car, because a conversion now costs in Brazil approximately 80,000 reais, so it's not economically feasible, let's say. But you have other points instead of just the money. It's like a quid that you can buy an electric one. Costs about 140,000 reais, and a combustion engine one you can buy for 70. So I 71 and keep the other 70 on the bank, and use as much fuel as I can, and that would last a few years. And probably the batteries from the electric one would go bad before I spend the 70,000. Depends on how much you work and how many kilometers you ride a day. So for a common person that goes to work and has to ride like 25, 50 kilometers, I'd say it's not economically possible to convert a car or to buy an electric car these days, with the price of the cars and the price of the fuel and the cost that's involved. But commercial vehicles that drive 24/7, it would be possible. So the project that I'm inserted on, think about that, and like the mail, the correios that we have here, the fuels that they use, they ride like 2 shifts of 60 kilometers, so they drive 120 a day. And if you don't buy the car, if you already have the car and you convert it, probably it's going to pay off. So you have a payback in, I don't know, 4 years, 5 years maybe. But to start with, conversion is also not so easy. People just think, oh, I'll just convert my car, a Celta Go or Volkswagen Beetle or something. But it's not that easy in Brazil, because you have to make the new document, and you have to do that for every model of each year of the car. So if you have a Fiorino, we are making, it's called the CAT. It's a process that you do in the DMV, in our DETRAN. It's the kind of Department of Motor Vehicles that we have here. So it costs a lot of money, and you can do that for one model year of a car. So you're doing that for a Fiorino 2016. If you want to convert that 2017, you have to do another one. So I think about it before doing it. We're doing it, but it's like just hypothetical stuff. We did like $1 million to convert 4 cars. So a lot of fuel.
If you were an Uber driver,
said.
Depends on how much coffee you have, because you have to drive a lot. Florianopolis, the average speed that you keep in the center of Florianopolis, you can make like, if you're fast driver, you can make like 40 kilometers an hour. So if you drive 5 hours, 2 kilometers maybe, but yeah, maybe coffee. Yeah, but like for a commercial use, it's possible to convert, and it's also possible to buy a new car, like a Jack, cheap, and a Kiwi, it's also cheap to do like kind of job, like for delivery or for taking people everywhere. It's possible, but not for like I drive 30 kilometers a day to go to work, so it's not feasible. Although I have an electric car, but it's a second life electric car. It was a lead acid, 8 batteries, 48 volts, with a Carter converter, and I'm upgrading it to lithium, and so it's a very common car in England. It's the Reva. It's the Indian car, 2008. So it's electric car, but it suits. But you have to do the math to make it valuable to convert the cars.
All right, I think we have one question. Augusto, we'll do that, and then you.
To you again. What do you think are the necessary steps that will allow this conversion technology to widespread, really? Because nowadays, I think almost nobody is thinking about this.
Well, we say it's not a Lego, because you can't just buy anything and assemble in the car. You can buy the battery pack that comes with the BMS. You can buy an engine, inverter, but you have a lot of other stuff to build in the car, and the assembly of the engine to the gearbox not so easy. So you have to do one for each car you're building, or at least for each family of cars. And the cars are not the same. As I said before, new cars in Brazil from 2012 on are very hard to convert, because you have the CAN and the communication inside the car that's lean, and that's all the communication that turns in the car. If you go in a newer car, you won't. If you take off the engine, you can't open the door, you can't turn on the radio, because it's all in the same box. And as you take off the engine, it will go to an emergency mode, and it won't start. So it's quite hard. And so the first step is to get the technology to do that, like a kit. Like for an older car is no problem. But the second stone in your way that you're going to face is the question that you can't just drive it in Brazil. You can get a license to drive one car. If you build one car a year, you can have a license for that car. But that's not usual. So everybody's thinking about doing a line of cars, like we are for the mail company or FedEx or Mercado Livre or whatever. They have, or they already buy or rent a bunch of cars from the same type, same model year. That's possible, but the law in Brazil to license those cars is quite hard to fix. So the first problem is the technical stuff to build a car. The second one is the licensing of the car.
Thank you. Question I have about, we talk a lot about maximization and utilization of power, distributed power, many spots, and being consumed other places. So the question is this, there's a lot of data exchange happening for you to get to that. How are you making your systems, you're communicating so much information about energy flow? How can you make this absolutely, let's say, proof? It's a real concern, I can see. Too many companies are using this blockchain or this sort of things. But again, they are again a problem, because they will consume a lot of power to every time you have to generate a string of data which you will send out. So the question is, how are you proceeding? How are you coping with this problem?
The easiest answer to the question is we are not caring about that. We believe in only good people. To be getting a bit more detailed, you have seen on the very left of those slides this smart meter gateway. And Germany is a developing country in terms of smart meter application. So when you look to the European countries, they are much more advanced. But one reason we are so behind is that our it's not a ministry, but it's a body of the government that looks for internet security. And they do a lot of tests to only get permission for smart meter gateways that are safe for hacker attacks. And as we try to use the information of smart meter gateways, I hope we do not need to care too much about those problems. But I'm absolutely, I have no expertise on this data security. Sorry.
But it's still a mission, so
yeah.
People are working on this. Just thank you for updating.
I have to comment on that, sorry. We are starting in cooperation with the lab in Brapi, so that's a kind of institution that will be able to do research, research institute. And this lab is part of it to try to attack this problem, because like we are using this lab as a model to try to test that, because we have a lot of data and we have a car, we have a battery, we have a lot of photovoltaic systems, and we have been hacked before. So if someone comes here, wants to hack us, just like keep us without energy for 3 days, they can, like if they are able to hack us. So it's an Embrapi institute focused on cybersecurity, on renewable energy. So we are trying to go on, face the challenge. Yeah, definitely.
Thank you. Gustavo, I think we have one more question over there. Here. No?
Oh, I have a question for Lucas. So I really like your presentation, and I like the overview that you gave of what you can do in the Amazon. So I want to know if you have shown an idea, a plan, or what can be improved. And I would like to know a bit now what Brazil is going to do actually now. So you are proposing some idea. Is there an exchange of how to put it in action?
Yeah, thanks. Yes, I bring a lot of questions, yeah, answers.
Yes.
But the idea is that a few of those points that I mentioned is starting in proposing a different way to have the new auction in the off-grid system, in the isolated system. This probably will be an important step in the Amazon energy transition. Yeah. So right now, what we have is basically auction model where normally you have a 5-year PPA if you are fossil, and a 15-year PPA if you are 100% renewable. So that's not the two options. I think that a good way to go to a transition is in between. So the proposal for the new options is to have at least a minimum amount of renewable penetration. Could be 50, 60, higher. It depends on how long you have the PPA. And basically, which is the source you're proposing. But we think that at least 50-60% need to be a minimum amount of renewable penetration to have at least a transition towards 100% renewable penetration in the near future. So that's our proposal, that's the goal. So this is basically the main results of a project that we are assessing together with EPE, mainly the energy research company here in Brazil, who is responsible for assessing ideas for the new auctions. And basically is the main contribution that us, together with the researchers and experts, are proposing towards this energy transition.
Thank you very much.
All right. Did we have another question there from earlier? No. Let's check online. You have any? All right. All right. Maybe we'll move on then and get an early lunch. So. Okay, and you may now be seated. Now we're going to hear a little bit from two representatives, Felipe and Rodrigo, respectively from IFSC and UFSC, just brief presentations on their projects and how they partner up with private companies and research institutes to do research with specific ways of funding. So Felipe, do you want to start?
Thank you. Hi, everyone. I'm going to be very brief. I'm also looking forward to lunch. And so I'm here today to talk about the EMBRAP unit, which was very good that we commented about EMBRAP here recently. And for those who do not know EMBRAP, it stands for Brazilian Company of Research and on Industrial Innovation. And as EMBRAP unit at IFSC, we are here to talk about partnership opportunity or R&D tonight. Please. Can you go on forward, please? Okay, so what we do, we work at research, development, and innovation projects that are made possible through highly qualified team. You could check some of the team we have here. Our Professor Van Dresden is one of the researchers acting at our EMBRAP unit, and sharing of risks between the interested company, IFSC, and EMBRAP. So that's the point that I'm gonna like to highlight to you, is that we need a company to have an EMBRAP project. We need to have a company involved. So we work at innovation that it's made to reach the market. Okay? Go on, please. We also like to highlight that as a federal institute, some of you may not know Federal Institute before. We are pretty much like the universities. Universities are very much associated to the idea of innovation, and a Federal Institute was born to innovate and give, to make, to reach, develop technical and technological solutions. So we like to highlight this as well. Go forward. EMBRAP work to connect instead, so EMBRAP work to connect the industry, the academia. It's very much like a triple helix model, focus on risk sharing, on pre-market innovation. So we like to reach the companies that want to make innovation and are maybe afraid of taking the risk. So EMBRAP getting in the team, getting the boat to finance some of the project and to make this risk takeable. As a standard R&D project, we have a company funding 100% of it. As an EMBRAP project, we have 2/3 of this, or let's say a third of it may be funded by EMBRAP with non-refundable financial resources, and the other 2/3 are shared between the ICT, or sorry, the S&T institution and the company. So that's the main differential here. You can make a R&D and I project with much less risks. As an EMBRAP unit, IFSC has smart energy system as a field of competence, which is divided in 4 main lines. The first of it is development of computed systems for energy market management. The second one, renewable energy sources. The third one, energy efficiency and smart grids. And the fourth one, urban mobility. So if you know a company, if you are interested in it, we are very much open to partner. Thank you very much.
All right, now Rodrigo from UFSC.
Morning, everyone. Thank you. Thank you for the invitation, Professor Samuel. And I think that actually I was not prepared to make a presentation in English. So my apologies for everyone, but I will try to do my best. Actually, Philippe told most of everything about EMBRP. So EMBRP it's an organization, national organization that could supply with the research inside the enterprise, sharing the problem and solution with the universities. I just focus on the difference in EMBRP Unity from IFSC to EMBRP Unity at UFSC. We work on 3 different areas with vehicles and mobility. Focus is on mobility area. So we work in projects like development of new projects on mobility problems. We can also work on energy conversion systems and energy conversion solutions. Actually, we also can work on manufacturing processes. We can actually develop new solutions or improve some processes that are not working so well. Make the enterprise more competitive in the market and something like that. You can go to the next one, please. More one, yeah. And have actually 2 different kinds of contracts inside the EMBRP. The first one is very similar with the IFSC. So it can EMBRP can give a third of the funds that you need to make the project. But the second type, next one please. Yes. But you can reach up to 50% of EMBRP participation, and that depends the size of the enterprise or even the structure of the partners. For instance, if you have a big enterprise with a small one working together in the same project, we can guarantee 50% of EMBRP participation. Then another one, the third, yes. And we have also another program called Sebrae Rota 2030, Rota 2030, that we have another organization. It's a federal organization to development of the small enterprise in Brazil. So they can put up to 300,000 reais in each project, and we have 3 different ways to make this kind of program. If you work with just one small enterprise, the Sebrae could finance 70% or 150,000 reais. If you have one small enterprise with a big one, can reach up to 70% of the part of the enterprise, or 200,000 reais. And if you have one small enterprise or even a startup and more than 2 or more big enterprises in the same project, you can reach 300,000 reais. Compared to another kind of for the enterprise development, The MRP is very fast. You can contract between 30 to 15 days between when you start the process inside of your university to the final assignment. And there's not a lot of bureaucracy involved in this program because the discussion about all the project is only made by university and then you have no other organization in this conversation. So it's very easy to contract. Actually, you have some discussion about industrial properties, but you have just a solution. You have a solution already defined inside your university that makes the things go very fast. So I spent 5 minutes or more. Okay, thank you very much. Bye-bye.
All right, so now I'd like to invite Professor Essa. He just wants to make a short invitation to you all for the workshop they're having next week at UFAM.
Hello everybody, it will be real short. I'm here only to invite you all to the continuation of this workshop. This one is the first part, but the next Wednesday, the second part will occur in Manaus at UFAM. Some of the people here will be able to attend in person, but everybody here is able to attend virtually. If you on this QR code, you can find more information, then you are welcome. Thank you.
All right, and I would like to thank everyone for coming and for bearing with us for this very long morning. And we are having lunch at Bariol, which is a restaurant with a 5-minute walk from here. And then for those who would like to participate in the tours, we're gathering here at the hall starting at 3 p.m. All right? Thank you everyone for coming.